Well, and welcome to SkyTour LiveStream for Wednesday, the 16th of November. How are you guys doing? It's nice to see everybody here. I love that everybody's here. And I want to welcome Daryl Mason to the stream. Hey, Daryl, what's happening? How you doing?
Hi, Mark. I'm good. You? Hello, everybody.
I'm fine. Daryl and I were talking just off the air about the Artemis launch. It really is a brave new world for NASA. The only one of the problems I have is they're using the old shuttle boosters, the old solid rocket boosters, and that technology for the outside booster launch. And we know what happens with those boosters in cold weather. They do exhibit failures. So I'm wondering what they did to fix that. I imagine they would have had to fix that. Pretty bad, you know. But you know what? It represents a new chapter in the human return to space in a lot of ways, right?
Yeah. The whole thing is recycled shuttle tech. It's 70s technology. And one I didn't know, they didn't even recover the boosters. They just fell in the ocean. They let them sink. That and the main engines, you know, on the main rocket body. That's 4 shuttle engines that they had in storage, spares from the shuttle program, and they're throwing away 4 of those engines with every launch.
Yeah, I think that's...
They're all gone.
I don't think that's wise. Okay. But, you know, let Elon Musk influence them a little bit more, and they'll get into reusability. You know, you don't complain about how much the launch costs, right? And they're probably saying, well, we've got these engines, we've got these boosters, let's use them up. Meanwhile, we'll work out a new technology that we'll then have to test. Well, I think they should have done that to begin with, to be honest with you.
I agree. I mean, yeah, let's use them all up, and then we'll get to build a whole new rocket program, you know.
And that's what's going to happen.
By the way, that launch cost $4 billion.
Actually, that's not bad considering that the shuttle launches cost $22.
Yeah, well, still, that's government work for you.
Yeah, but still, it was better than $22 million is, you know, a lot more expensive. $4 million was actually a very cheap price. If you're telling me that's how much it costs. Hey, Sean Farr was here. Hi, man. What filter app? What do I need for my phone? I want to observe light-absorbing material in space. Not sure what you mean by the question, but try that again, and we'll answer it for you. You know, I also want to say hello to PG, who was here first. Hiya, Petita. Nice to see you. And Fantasy was second in the door. You were third in the door, Daryl. Dean Bustador was here. We have Daisy and Zoe Amethyst. Good to see you guys as well. And we had Izabela. Hi, Izabela.
Hi, Izabela.
Yeah, we always say hi to Izabela. She'll get mad at us if we don't, you know, and she deserves to be greeted because, you know, you all do. But she's always doing our table of contents stuff, so it's probably a wise idea just to, you know, let her know that we appreciate it, right? It's important.
Sure. Izabela's going to be running this joint one of these days.
Yeah. And Cyclone has changed the name from NPC. Nice, man. I like that name. Because NPC means non-player character, but you're playing, man. You're in here. You're doing stuff. So that's it wasn't the name that suits you, man. So that's a good name. All right. And we have Alice Pooper. Nice to see you. And Bonnie Anahata 77's with us. Hiya, Bonnie. And Wayne Pinkham. I have to show you the shirt that Wayne Pinkham brought me back from Mauna Kea. It's really amazing. It's a great shirt. Wayne, I wear it all the time. Probably more than I should. It's a beautiful dark maroon shirt, a t-shirt. And it has the Mauna Kea logo in the top and the front. But in the back, it shows all the mirrors that are on Mauna Kea right now. The Gemini telescope and all the other telescopes up there in their comparative sizes. It's really cool. Probably the best shirt I've ever received from anybody, and it was total surprise, man. Wayne was great. Thanks, Wayne. That's a public.
I have a model from Mauna Kea Observatory. The plant manager I used to work under, he married a Hawaiian girl.
Okay.
and he was over there a lot. And they visited the observatory one day, and he got me a really nice. It's one of those big blue Nalgene bottles,
Oh
Nalgene,
yeah, yeah, yeah. Of course.
and it's got the Mauna Kea logo on it, and
Wow.
it's really a super bottle. I can see it from here.
Actually, a friend of mine brought me an empty Apollo beer bottle that was that blue Nalgene glass. It was really cool. Roni Hassan, Tim F, how you doing, guys? Good to see you. And I see Mike, Aberration of Light. How you doing, brother? Good to see you as well. And Farva's trying to clarify. He says, let's say there's a rock in space that absorbs light. Okay, that's true. They will absorb light. But you would need, I think you know what you're asking. You're asking if you can do spectral analysis on your iPhone or on your Android phone. And the answer is only if the light coming to that phone is first processed through a telescope, because anything you're going to look at in space is going to be really, really tiny, and you won't be able to see an adequate resolution detail of that spectrum unless you actually have a good telescope with a fairly high focal length or ability to magnify the view. So I see what you're getting at, and that's actually good thinking. I do have a spectral system over here. You can't see it. It's over here, and it's one thing that we're going to install, I think, on the telescope behind me, and that'll be out here. I talked to the contractor today who's going to build the steel armatures required for our roof that's going to tip off of our building. The roof is literally going to be lifted up and moved to the side and down on the new observatory for the East Coast. And this weekend, the SkyTour LiveStream folks in Arizona are scouting another location for observatory number 3. We are trying to move as fast as we can because, we want to get as many observatories online as soon as possible. We want to have a whole network available, so there's no excuse for missing a night. Okay, and we're going to actively seek people that can run the telescopes from their locations as well to make it. And Daryl, of course, you will be one of them if you want to. And I'm working on a manual for how to do things and what order to do them in. And I'm trying to make it, robust enough so that you can't make a mistake, because everybody makes mistakes.
What?
Marianne
is here.
Oh yeah. Wow. Well,
hi, Marianne.
I like that. That's good. Hey, Marianne.
I'm not sure I'd want the weight of that on my shoulders.
Well, if you can't hurt it, I think you'd be okay with it.
If I can't hurt it, yeah.
Yeah. So that's what. Okay. Give me an example. Look at the telescope right now. See right there? Okay. The telescope is sticking out. It's sitting up high enough so that if the roof were to close right now, it would hit the telescope and probably cause a few $1,000s of damage. There goes a Starlink satellite. Well, we would want to make that impossible to happen. It's written in the code now. I can't close the roof unless the telescope is in the parked position and below the sensors we have in there that detect whether there's something above a certain height.
Yeah.
So we're set with that right now. So that you couldn't do that even if you wanted to.
You need a robust operator's manual.
Yeah.
And probably a troubleshooting guide too.
And a robust operator. Yeah. So as you can see, this is the double cluster. This is our opening object for tonight. And it's really pretty. And I haven't done any exposures of it other than this live 1 second shot. And just so to review, this over here up top there, that's the telescope control system. This is the telescope computer. It's guiding currently on the cluster. This is the telescope in the dome. This is me. Hi. And over here, right here, is this is a link to SkyTourLive.com. It's not a link actually you can click on, but go to SkyTourLive.com, and that's the portal that leads to everything SkyTour LiveStream. It gives you access to our database for free. There's no tricks or anything here. Everything we take is available to you for free. And then over here is the main view. and we can do things like make that view larger, okay, and make it smaller, and bring me back to be able to see my telescope here, okay, if the gestures will listen. And then this is our camera control system over here. We have the most important things are the exposure. All right, right now it's 1,000 milliseconds. That's 1 second. We measure in milliseconds. And then the gain. Right now the gain is at 350. The gain can go to about 500 and 0. So 350 is a reasonably good starting point. Marianne in the chat, by the way, says, hello, heading to southeastern Arizona for a good dark possible location. Yes, she is telling you what she's doing. She's going to be heading down there to scout this new potential location for us. And it's going to be a dark sky site that is actually better than this one that we're in. Can you believe it? Yeah, really interesting. So let's bring the cluster. Let's head a little west right here. Pull us in a little more.
Double cluster is what we ended the stream with last time.
I know. That's what I figured we'd start with. Yep. So it's kind of cool. And let's zip us a little south to pull it above the label there. Here we go. All right. And Izabela says, I have a presentiment of a wonderful night coming up with great observations. What's a presentiment? Do you have any idea? I don't know.
I think she means presentiment.
Okay.
Presentiment. Presentiment.
Maybe so. Hey, Jessica S. Izabela, you're right. We're going to have a good night tonight. I was looking at a few objects last night. I just did a private stream just to check out objects because on nights we're not streaming, I'm still doing work. And I went out and I explored some other objects we might be able to look at. And there's a couple that I think are really interesting. Daryl had suggested one called the Wolf Cave Nebula. Wolf's Cave Nebula. And I did it yesterday, and it's really not as good as we wanted. It's dim, and in other words, it's not good for this type of environment. If I did it and did 10-minute exposures, yes, then it would be beautiful. But I'm not doing 10-minute exposures. I'm doing 30-second to a minute at the most exposures because I have you all as an audience that wants to watch and learn and see things, and seeing the same thing on the screen for more than 5 minutes, it's, to me, just too much. So that's why I try to change it up a lot. If I'm not seeing anything interesting about the things, then I like to change it up. Okay, so let's actually try to do something with this so we can save this. Let's do a 25-second shot of the double cluster. And here we go. We'll set it off and running. Okay, and we'll go into our live stack. And this was the Funnel Cloud Nebula that I tried also. And it needs more exposure time. This is fine. We can still try it. Let's pull that out. All right, so 25 seconds, we'll see the double cluster now. And it's really kind of neat because this is a cluster where one of the components is much closer to us than the other. I mean, look at how rich they are. But this cluster is really much closer to us, I think, by about 1,000 light years, I think, in this one. And so you're seeing them like this, okay? You're seeing one back here and one up here in the foreground, okay? And so the one in the foreground is, well, I should do it this way. It's just the one on the left, right? So this is the one that you're seeing on the screen, and then you got this other one back here, all right? But they just happen to be line of sight, so they actually look like they're right next to each other, but they're not. Yeah. Okay, so it's a 200 light year difference. Is that what you said?
That's what Wiki says.
Okay. Yeah.
7460 and 7640.
Yeah. Okay.
180.
So you can see, and we commented yesterday on how these orange stars appear in here as well. But these orange stars are not part of these clusters. If they were, then these orange stars would kind of break the mold of our understanding about how clusters form, because the stars that form in clusters are pretty much all the same kind, right? Because they're forming at the same time from the same material, so they generally tend to be the same mass. And so the variance in the mass might be a little bit, but you don't get like hot blue stars formed with, orange stars. You get stars that kind of form of the same type in the cluster. They're hot and they're young. But it doesn't mean you can't have a red star that forms out of nowhere. You can. You can have multiple red stars, but they're all formed from the same amount of material. It's a strange way the universe works, but there is variation among these stars. They're all different masses from each other, generally. But chemically, they're all the same. The composition is pretty much all the same. I think I told you when we looked at when we look at the sun, we see a star that has a particular composition. It has a specific chemical signature in its spectra that tells us what it's made of. And we know that if we find another star that has that exact chemical composition, that's a star that was formed with us at some place in the galaxy, wherever we were at the time when we were formed 4.5 billion years ago. And we found that. We found at least one of those stars. It's in a southern constellation, I believe. I don't remember which one. Maybe down in Vela. I'm not sure. Well, either way, that star is a sibling of our sun. It's almost exactly the same composition as our sun. And that's something that's really interesting about these stars. I want to say hi to Jeremy is here, and we have Mike Hedrick is with us. Hi, Mike. How are you? And Alabama, how you doing, brother? Alabama Constitutional Crusader says it all. Nice, man. So that's cool.
Double clusters, OB stars.
Yeah. Hot and young.
The core of the Perseus OB1 association of hot young stars. And that's a reflection too on the difference between the cluster stars and those red stars. Those red stars are going to be older.
Yep. Well, they don't necessarily have to be older. They could technically have formed as red stars and be about the same age. That's the problem with the universe. We have to actually study the evolutionary state of these individual stars to know when they formed. But you're right in general that when you see a cluster like this, okay, they're all together. These red stars aren't really together. They're already outside of any potential cluster they formed in, so that's sort of a clue, right? That maybe they're older, like you were saying, and that's a possibility. But we don't know for sure, right? We can't say definitely because our sun formed with at least one other star.
But you see, 884 includes 5 prominent red supergiant stars, so they're probably pretty evolved.
Yeah, if they're supergiants, then they're going to be, so they will be older. But the littlest red dwarfs might not necessarily be older. They could have formed around the same time as these stars in the cluster at a different location, with a different different mass. But it doesn't mean anything else other than if you know that they're supergiants, well then you know that they migrated to that phase. They went up something called the asymptotic giant branch after they left the main sequence where stars fuse hydrogen into helium.
Yeah. Well, it says 5 prominent red supergiant stars, all variable, all around 8th magnitude.
Yep.
And if they're anywhere as close as as far away as the double clusters are, they sound sort of like Betelgeuse.
Mm-hmm.
Variable red supergiants. They're dimmer because they're 10 times as far away.
Yeah. I see Dave Schmidt has a question you want to ask about gases. Sure, go ahead, David. Ask away. Hey, Marco, how are you? I'm glad Alabama is good. Thanks for that, Alabama Constitutional Crusader. Okay. We're gonna... part of the reason I'm doing this stack right now is to just check the winds, because when we looked in this direction last night, if you remember, or the other night, when we were pointing in this direction, we had winds that were affecting our view. And right now, if we zoom in, there's only the slightest problem. In fact, it's hard to even say there is one. It looks like it's pretty good. So, but look at this. These are stars. Let's pull this over here for a minute, okay? Check that out. Isn't that cool? Let's get rid of this window for a minute. All right, as well. I want to get rid of that. There we go. Look at this. Oh, to live among the stars. This is a gorgeous, gorgeous, absolutely gorgeous collection. Just beautiful. Oh, man. What do you guys think? Can you imagine that 20 by 30 printed on metal on your wall? Wow.
I see 5 red supergiants.
You see 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, right? Little zigzag pattern.
Yep.
Wow. There's one up there too. It might not be a red supergiant, but it might be. I'm not sure which star that is.
David, as a general thing, gases will mix. When we look at various nebula, emission nebulas, we may see places that are predominantly O3 or oxygen 3 or predominantly hydrogen 2, but gases, I think, will readily mix.
They do, and that was your question I see from before, David, okay. David asked the question, the other day we saw some nebulae with different colored gases. Are there some gases that won't mix, or is it a matter of how dense they are in certain areas? That's actually a very prescient thing to say, David, because the density makes a lot of the difference. Let's suppose, as Daryl says, the gases have mixed. You have hydrogen and you have oxygen all mixed in the same place, right? Well, if the hydrogen is much more dense than that red hydrogen 2, the color of my light here, okay, that's hydrogen Roman numeral 2, HII, right, H2. That particular ionized state of hydrogen will dominate the light you see. Because remember how that light forms. What's ionization, right? Ultraviolet light hits an atom out there, and the electron is absorbing energy and leaves the atom, ionized state. So now you just have a proton, which is the hydrogen nucleus, right? Then the electron, bumping into things out there, comes back in, it loses energy, it gains energy to leave, but then when it comes back in, it cascades down a ladder of different energy levels until it finds a spot in the atom again, falling to a particular energy state. Each time it does that, it gives off a certain amount of energy. That energy is in the form of light. Well, the predominant place that a hydrogen atom in this particular situation will drop to is the second level in an atom. We call it n equals 2. And that n equals 2 level is the transition to create hydrogen alpha, or the H2 regions. It gives off red light. It's a longer wavelength red light that it gives off. The similar problem, and I leave it to you to think it through, happens with oxygen 3. Now, O3 is a doubly ionized oxygen atom. Now, why isn't it a triply ionized oxygen atom? Because it says O3. Because we leave off the Roman numeral 1 on all the atoms. Okay, that's the ground state where they have all their electrons. And it's just easier to say hydrogen rather than H1. Okay, so that's why an ionized hydrogen atom is H2, not H1. Okay, because it's already H1. Similar with oxygen, O1, O2 is Roman numeral 2, doubly ionized, triply ionized, okay, etc. So a doubly ionized oxygen atom is O3. Okay. Anyway,
which is more energetic.
Yes, and that color, when the electron recombines, is a greenish blue color, which we see a lot of. In fact, we might see some of that tonight if we go do the Lion Nebula Daryl?
I would wonder if,
Maybe.
I'm assuming at this point that hydrogen, ionized hydrogen, when it emits, hydrogen alpha radiation, is lower energy than the O3. I would wonder at certain energy levels that, you might see the hydrogen emit before you would see the oxygen emit. Therefore, you know what I'm saying, that you might see a prevalence of hydrogen. Maybe you already said that. You'll see the hydrogen before you would see the oxygen, and maybe that would make it more prevalent.
Well, I think that it's a matter of, as David Smith pointed out, it's a matter of the density of the gas and its ionization potential, and whether the star nearby can easily ionize lots of hydrogen. Okay, now the ionization energy required for oxygen, okay, is going to be a little different from the ionization energy for hydrogen. So if the star gives off just the right amount, it might not potentially ionize all the oxygen, but might ionize the hydrogen very well.
Yes.
So there's so many different factors here. But David's comment was a very good one about, does it depend on the density? Because in general, that's what it depends on. It depends on the density, because we assume the star is hot enough to ionize anything. So if that's the case, then, what does it ionize? Well, it ionizes everything, but if the hydrogen isn't very dense, but the oxygen is, you're going to see the O3, greenish blue nebula. You're not going to see the red one. It'll be buried in the green, or you might see a mix of the two colors, like we see in the Running Man, where you see a reflection nebula, which is non-ionized but just dust scattering starlight, but inside there's a H2 region that's giving off red light. And in light terms, when you have a red light going through a blue light, you get a magenta light. And sure enough, that part of the Running Man Nebula that we'll see in just another month or so with Orion, it looks magenta. It doesn't look red like it should. And I think that's pretty cool. And people usually correct it to the wrong color, thinking it's supposed to be red, not thinking it's going through this dust particles that are already scattering blue light from the star. So it's pretty cool.
I would wonder too, like when we look at planetary nebulas, like the Dumbbell as an example, if the different gases were emitted at different points in time, thus some is farther away than the other, that might be part of why we see, green with red around the edges.
That's
blew
certainly
off the hydrogen first, and
certainly
off the oxygen later.
Certainly, that's probably true to some level. Or that outer shell is denser in hydrogen than it is in oxygen, and so you see that. But see, I haven't looked at, say, let's pick the Dumbbell. I haven't looked at the studies of the Dumbbell Nebula and looked at the chemical composition of the nebula. It's very, very complicated. It's not just hydrogen, as you know this. It's not just hydrogen. It's not just oxygen. There's all kinds of things in the Dumbbell spectra, and you're seeing the spectrum of all the things that made up the original star that sloughed off in the outer layers. It wasn't just hydrogen. It was all of the material getting blown out and pushed away over time. So we've stacked 35 frames here of the double cluster. I mean, this is like a jewel box, isn't it? And the guiding is absolutely spot on, perfect. So I think we're good to go to a couple other things now and check them out. But we'll save this, because why would we not? This is probably just a most beautiful open cluster. I marked it as double cluster OC, as you can see right up here. And maybe you can see that, maybe you can't. It's kind of tough to see it. All right, and then I'll go into the stack and save it, and that's going to save the astronomical FITS file. All right, and you can view that with a free FITS viewer if you want, or you can just take the save exactly as seen ping, which is this file that you see right there. And when you click on that, what you'll end up seeing is this guy. This is what you get, right? This is the actual file that you'll get of this, and then you can do whatever you like. You can have fun. You can zoom in on things. Look at that. Check it out. Blow it up. Have fun with it. Okay, and that's all available 100% free. We don't charge for our images. If you want them printed or whatever, you can get them from SkyTourLive.com and get them printed. I had a couple people actually buy some more the other night. So feel free. All of the money goes to SkyTour LiveStream. I don't take any of it. I don't make any money on this, which is sad. I should probably try to make money at this, huh? But as soon as you mix money with your passion, it doesn't become a passion anymore. It becomes work. And just, I'm not into that. You know, I really want, well, I'm into work, but I just want to make it happen the right way. Okay, so let's get out of our stack here. And we've saved it now. And we're going to go into, make this our 1 second night vision view again. So here's our night vision view of the double cluster. And again, it didn't do the 1 second. It kept going. It does some weird things. It has some bugs, this program. This is going to look right. Ba-boom. Yeah. Okay. Ba-ba-booey. All right. So now we'll zoom out and we'll do that. Let me just, here we go. That's more like it. Okay. Let's go into our planetarium program. First, I'm going to move us a little bit to the west. Here we are. And now I brought in some of the catalog objects too because they're really cool. But the first thing we're going to do, because it's right nearby, is we're going to do the Soul Nebula, because we did the Heart Nebula the other night. So we're going to do Soul right now. Heart and Soul forever, right? This is going to be a stellar nursery where the stellar cluster in the middle, with their powerful stellar winds, has literally pushed all the hydrogen gas out of the center and made like an empty cavity. These stars do that with these nebulae. They make cavities, cavities that are empty of a lot of gas and so forth, because the stellar winds are so powerful. I want to say hi to Claudio Ramos, who is with us from Chile. How you doing, Claudio? Nice to see you.
May I answer Alabama's question?
Yeah, okay, sure, go ahead.
Alabama, the Leonids, you won't see any until the constellation has risen. The radiant point is inside what's called the sickle of Leo, and the sickle of Leo rises right about midnight or a little after midnight, depending on where you are in your time zone, maybe a little earlier or a little later. It looks like a big backwards question mark, about as big as your hand at arm's length, and the bright star Regulus is the dot at the bottom of the question mark. The radiant is a little bit above Regulus. The peak is actually tomorrow night.
Right.
And interestingly, some people are predicting there's going to be a surge on Friday night or early Saturday morning. It's going to be best for people on the east coast of the U.S. The Leonids are typically a very, it's only about 15 meteors an hour most years, 15 or 20 meteors, except during storm years, which is about every 33 years. But they're saying that the Earth may run into a stream of meteors that was given off about 300 years ago on Friday night, Saturday morning, actually about 1 a.m. Eastern time. And they may see several hundred meteors an hour that night. But the predicted peak is the evening of the 17th, morning of the 18th.
Yeah. Well, it should still be pretty interesting.
Oh, the second best thing I ever saw in the night sky was the Leonids.
I once stayed up hours and just waited and waited. And I was not disappointed, because when I looked up, I was sitting in my living room looking through the big picture window, which looks over the lake up here. And I looked up, I just looked up in the sky at the right moment, and I just saw this beautiful beautiful meteor go by with a trail behind it, a train as we call it, of ablated particles, so basically smoke effectively. And it was stunning. It was absolutely stunning. And that trail stayed in the sky, and it ended up twisting and turning over the next few minutes to just sort of like disperse in the sky. It was really pretty.
We saw one like that in 1999. The Leonids put on a heck of a display for 3 years in a row, I think it was.
Yeah.
98. I was driving down a back road out in the back end of El Paso County here, way out in the middle of nowhere, and Leo rose right in front of me.
Oh.
And the instant the sickle rose, it looked like somebody was shooting Roman candles off. They were just streaming right out of the radiant point inside the sickle.
Wow, that's neat.
And all sorts of colors. It wasn't a storm that year, but there were tons of bright, colorful fireballs. In 99, we had a heck of a, it still wasn't the storm, but we had a heck of a shower that year. I viewed it with the astronomy club out in the country, and we were all, we were laying on blankets on the ground, or I had Chase Lounge with me wrapped up in a sleeping bag, and I got so cold and stiff I had to get up. And, you know, when you're cold and stiff and laying in a Chase Lounge, it's kind of hard to get up.
Yeah.
I had just rolled out of this Chase Lounge. I was on my hands and knees facing the ground, and the best fireball of the night went off behind my head. I managed to miss it. Everybody just, you know, ooh, wow.
What'd I miss?
It looked like a flash bulb had gone off all around me. It was so bright.
Yeah.
I managed to miss it. But the train it left behind, we watched that thing for half an hour.
Yep. Takes a long time.
As the wind slowly, you know, spread it out and it disappeared.
Yeah. They tend to go away over a long period of time.
Yeah. The next year was the year of the storm. There were thousands of meteors an hour. Everywhere you looked in the sky, there were meteors constantly. And that was the most amazing thing I ever saw until I saw the solar eclipse in 2017.
Wow.
They just, everywhere you looked, meteors constantly. It was amazing.
I think that's a really cool thing. I can't wait to see. I've never seen a meteor storm. I've looked for the Leonid shower, which is rumored to be one of the best ever since I was a kid. And I've never seen a meteor storm. And they always say, maybe this year, and it was never that year, never that year.
It has a 33-year peak. The Leonids come from a comet called Temple Tuttle.
Yeah.
And the comet has a 33-year period around the sun. And whenever it comes back around again, it sort of reseeds the area.
Mm-hmm.
And if we're lucky, the Earth is going to fly through that fresh area. And instead of 15 or 20 meteors an hour, you may see thousands of meteors an hour. Some of the historical Leonid showers, like 1833 and 1866, I think it was, they saw like 200,000 meteors an hour.
Wow. Well, the East Coast is the best place. Now, before you ask me if I'm going to stream that, I have a camera with a wide-angle lens on it, and the only problem I have is I don't have a USB cable long enough to run from out there in the front here on the East Coast to in here. But I'm going to try tomorrow to set up a system and actually stream the Leonids. It'll be tomorrow night that'll happen if I do it. And it'll be a wide angle, not a wide angle, but like a 50 millimeter lens. You'll have a pretty good 70-degree view of the sky.
Yeah. The predicted peak, although it's tomorrow night, it's actually early in the evening as seen from the eastern U.S. And Leo won't even be up yet. So don't let me discourage you from going out and looking tonight after midnight. You may be as likely to see them tonight as you would tomorrow night.
Yeah.
But the general peak happens the night of the 17th, 18th, and then that possible surge is going to happen the evening of the 18th into Saturday the 19th. Hello, James.
James Dugan, good day. James is
And
from
hey,
Australia.
Star Baby.
Yeah, and Cindy Murphy's with us. Hi, Cindy. So yeah, so this is the Soul Nebula, and the Heart Nebula is just above it. And we've done the Heart Nebula the other night, but we didn't do the Soul. I didn't do it on purpose. I wanted to, not do the Soul, not do the Soul and the Heart together, because you need time, for both of those. And right now, because we get just a beautiful evening, and I'm checking here when I come in here and looking at our view inside this beautiful nebula, you can see that everything looks really good, especially this beautiful dark nebula. Looks like a dog's head sticking out from the doorway or something. This is an area where the interstellar medium is particularly dense with dust. Okay, and it's in those areas which I've talked about so often that the universe forms stars, and that's where the stars are basically formed. They're inside those dark areas. Then they burst to life and they light them up, like over here. This was all dark nebula, okay, before it started glowing from the ionized hydrogen, and before the dust was illuminated by starlight and or scattering starlight. So it's pretty interesting. Now, what's interesting about this particular nebula is this cluster right here. This young hot cluster of stars is responsible for hollowing out this interior space, as you can see here. Okay, there was not uniform, but there was a relatively uniform amount of dust and gas in here. But as this star cluster formed in here, its powerful winds kept pushing this material out. You'll notice it's not a perfect sphere, and that's because the interstellar medium isn't perfectly uniform. Okay, it's not homogeneous throughout. Okay, so that means that in some areas where the stellar winds were impacting over here, well, the interstellar medium was already pretty dense with other material in here, so it couldn't push that material as fast and as far, but it did ionize a lot of that hydrogen out here. Similarly, over here, it wasn't as dense, and it pushed it out. Notice it's on a curve. See that curve? You can literally see how that's like a bubble being blown by this hot young cluster of stars. Now, it's in 3D, and we don't see it in 3D at this point, okay? Obviously. But you get the idea that you're seeing this part of it, if you look at me down here, but it really is going all the way around like this, right? So you're getting that happening, and so we see part of that edge that's being blown away from that central cluster. And you know what's going on with that cluster pretty much by looking down here. Okay, I'll show you. Right here, okay, inside, and we have to wait for, let me see if I can actually clean this up a little bit. I'm going to add a little bit of sharpening to this, make it a little more clear, and then I'm going to come over here and take us off that zoomed location, and I'm going to just do this. Actually, I'm going to pull it back a little bit. I'm just going to make this a little bit easier to see for you here. That's getting better. Okay, there we go. Okay, so you see this stalk right here, this bump, like that, and you see this one, you see this one, okay. Look at where they're pointing. They're all pointing up at this cluster. See that? They're pointing at this cluster because this cluster is sending a massive amount of ultraviolet energy from these hot young stars down here. That energy is ionizing the hydrogen gas in this region, but it's also, these stars have very, very powerful and copious stellar winds. And these stellar winds are pushing material away. But where the material is dense, like at the right here, and right here, and right here, it's not able to push it away at the same speed as the other less dense stuff. So it forms like basically a impact point for that stellar wind. It hits here, doesn't evaporate this very well, and so what's behind it is protected just a little bit. So that's why this stuff has lasted. All right, how long it lasts is anybody's guess, because it matters what happens to these stars and where they end up going. But that property is something we see in lots of nebulae. You see it in the Rosette. You see it all the way across this nebula, which is a few light years across. Okay, so we see a lot of that happening. All right, here's another stalk over here. All right, look at that. All right, so that's also, and then it may not line up directly, but that has to do with the other stars you don't see that are also giving off ultraviolet light in the background here that might be young and hot inside this dense cloud, so forth. So you may not see it.
I have a question.
Yeah.
If you look at this, if you want to call that a cluster there on the mid-right of hot young stars, is this what one of the double clusters would have looked like earlier in their evolution?
That's very interesting, because I often have talked about that in the past, because a star cluster forms inside lots of material. And so that lots of material that they form within is going to be dust and gas. So at some point in the past, it's very possible that the double cluster had a shell around it of material that we could have seen, but it has since scattered it and blown it away. Okay, this nebula is young, and it's actually in the process of scattering. As I said, it's hollowed this out, and it's going to keep going. And remember, everything is in motion around the galactic center. So these stars are moving around the galactic center, and they're also moving around each other, doing this around each other from mutual gravitational orbiting of themselves. It's the classic n-body problem, solved for all that complexity of motion. Okay, but as Darrell said, okay, was it possible a double cluster was formed that way? Yes, it is. And because they're hot O and B stars, it means that there was an awful lot of mass, an awful lot of hydrogen that was visible and there at some point. But enough time has passed so that hydrogen gas is no longer within the ionization range. It's been blown away, or the cluster has migrated as a whole out of the location it was in before. And that's very possible. We see clusters that are all alone, sitting in space. You go, wow, look at that. We'll see one when we look in Puppis, the constellation, which is east of Orion. And we'll see some there that are just clusters sitting there. M41, Messier 41 in Canis Major. And Messier 46, which is in Puppis, I think, which is the one with the M47, which has the little planetary nebula in the foreground.
How about the Pleiades?
Well, the Pleiades, yes. I mean, the Pleiades we're going to see first. But the Pleiades are hot O and B stars, or actually B stars, like what we see in here, okay? But they're only about 400 light years from us, and they're traveling through dust. And that dust is being made visible because of the fact that the dust particles are scattering the blue light from the stars.
Well, yeah. I know they used to think the Pleiades were, in that cloud, and now they're just traveling through it.
Yeah.
But is some of the nebulosity, the nebulas we see around a few of the stars, they have that combed appearance to them. That's not native nebulosity?
I think that's nebulosity that's influenced by the stars, but it's native to that region of space, and the Pleiades are the interlopers moving through there, and that those dust particles are scattering the blue light from the stars. Undoubtedly, those stars are going to interact with and form changes in the nebula's detail. Obviously, if they're passing through the cloud, they can't help but have an effect on it with their gravity and their radiative energy too. So
per my question about this compared to the double cluster, It's all a matter of how old the cluster is. I mean, this one is younger than the double cluster, and it's probably younger than the Pleiades as well.
And probably the lagoon.
Okay.
Because the lagoon cluster, I mean, if you're asking about the double cluster now, okay, the lagoon is going to probably be younger than the double cluster just by looking at the morphology, what's happened over time.
Absolutely.
The universe tells a story, guys, and so by looking at different objects and understanding how stars form, how clusters are made, you can actually come to some very reasonable conclusions about the interstellar medium and how things are made. And at when they were made. That's really kind of the important thing. That's what we don't know. That's what we had not had for a century until we started getting more detail on things like this. We stacked 23 of these. We're going to do 24, and this will be the 24th. That's good. I think that's good enough. All right, let me change the name up here. This is the Soul Nebula. Why it's called? Go ahead.
I'm sorry.
No, go ahead.
Back out so we can see the whole baby.
Yeah, right. I will.
I like the baby.
Yeah. Here's the head of the baby. Daryl's saying right here. Let's move it over. Here's the baby's head. There's the eye. There's its mouth. It doesn't look happy. Okay. Here's one of its hands. The other hand is probably up here. Here's the arm. Here's the back. Here's that big belly. And here's one of its legs with its feet, and the other leg is over here with its feet. So that's why Daryl... Oh, and look. It has a little tail, just like a human fetus does until it gets absorbed.
Star baby.
I guess so. Interesting. And I always thought you were referring to Cara Delea in 2001: A Space Odyssey, but you weren't. And I thought that was funny, too.
Well... it can remind one of that too.
Yeah, except you got to turn it upright, and have its big eye open like this, going, "Oh, look at the Earth." In the book, the Star Child, when it came to Earth, was going to come there to destroy it or do something to it. I can't remember, but it wasn't something that was going to be pleasant.
It's been a long time since I read the book.
Yeah. Okay, well, we'll save the Soul Nebula now here. And we'll save it exactly as seen. And then we'll clear it. We have it out there now. It will be up on the database in literally probably 30 seconds. And that's the other thing, too, for those that may not remember, SkyTourLive.com here is where you can go to actually access all those photos for free. You scroll down the first section, I think it's gray, and it says take me to the really cool photographs, and you click on it and you go drilling into the file folders there on our free server that we make available to you. And we have over a year of observations of all different phenomena out there that you can check out and enjoy. That's for you to just check out, man. No charge. I think it's just so important that somebody tells a story about astronomy and gets it out there, And I'm happy that you want to do it with us, Daryl.
Me?
Yeah. You certainly want to do it. Otherwise, you wouldn't be here every night.
Well, yeah, sure.
There you go. All right, let's see.
Some people, if they don't know any better, the astronomy just sounds like some sterile thing that nerds do, but I do it for the beauty of it.
Who are you calling a nerd?
You. Me.
Yeah. I know, I have my Clark Kent glasses, yeah, you're right. I'm a nerd. And you know what? I'm a nerd, and I'm proud of it. Yeah. Okay, there's our Soul Nebula. Now we're going to go check out... let's go to this little guy, and I'll tell you why. Because we're going to go check out a cluster of stars, again, that's sitting all by itself. And it's really kind of cool, right? It doesn't have very many stars. But I want to show it to you just because it's a star cluster that actually makes a lot of sense here to illustrate here with you. Let me just show you. Here it is. This guy is called the Jolly Roger cluster. And why Jolly Roger? I haven't got a clue. But its actual designation is NGC 1502. Okay? And 1502 is this little cluster. They call it a poor cluster. It only has about 50 stars. But check it out. Let's look at this. Okay, when you zoom into this, I can see we're going to do a focus again because our temperatures dropped quite significantly and I forgot to turn on temperature compensation. Okay, let's do that first. Okay, this cluster is another cluster that was formed inside of a hydrogen cloud, and the stars were probably hot enough to ionize hydrogen, and if they did, they've blown it all away out beyond the radius from which the cluster can ionize the gas, or the cluster as a whole has migrated away from the dust cloud and the gas cloud from whence it was born. Let's first do our focus run again, then I can turn on the temperature compensation. I apologize, I forgot to do that. But for those that like to follow and watch this system in action, this is our focus assistant setup. We're going to go in multi-star full width, half maximum, and we defocus. You see each of these is a star that's been assigned to the focusing algorithm, and then we're going to scan inward, and as we do, you're going to see more stars get selected, and as they get selected, you will see these boxes appear around them, and it's building a curve, right, a parabola, and you'll see the curve come down here and go up the other side, and then the center point of that curve is an interpolated location where it will go to find the perfect focus for the telescope, and then it goes there. And man alive, to do this from 2,500 miles away is a godsend, I gotta tell you. Daryl, do you remember the time before we actually had the ability to have the telescope look anywhere in the sky and figure out where it was just by looking at the pattern of stars? Before we did that, do you remember how we actually had to hunt for something we knew and then set the coordinates? Sure. Oh, very, very cumbersome. That was originally how it started. And then I added a feature called plate solving to the system. And it just meant, to me, that was sort of like a black box. I had no idea what it was doing. I heard the term, but didn't really know what it was because I never had to deal with it as an astronomer. Okay, the telescopes always knew what they were doing. They always had their place in the sky. So when I actually started doing this for myself, I didn't know what a plate solve was. And, I did it manually when I was using bigger telescopes in observatory buildings, professionally. But once you did it, you didn't have to do it again for years, So that was interesting. Okay, we found our curve. There it is. So now we go to best focus. So adding plate solving to this system was one of the best things I ever did because it ended up giving us the ability to literally, if the telescope went out of whack or we lost its place, which has happened, we didn't have to worry about it. We could just say, no problem, just plate solve, figure out where you are.
You and I both started astronomy before go-to telescopes were a thing.
Yeah.
I mean, back in the good old days, you looked at a star chart.
Yeah.
You saw something you wanted to look at. You identified notable bright stars or whatever in the area, and you star hopped your way to the object.
Well, that's right. That's what you did as an amateur astronomer, and that's true. When you're doing it professionally, that whole thing was already done because when the instrument was installed, it was aligned properly, and the bigger the instrument is, the more likely it's going to be fully aligned when you get there. Mine was. I used several systems. I used a 24-inch Cassegrain. I used a 20-inch refractor. The 20-inch refractor, the whole floor moved up and down to meet the telescope because it was like 30 tons of telescope over your head. And so you actually had to move the whole floor was an elevator. And I usually worked from midnight to dawn in the middle of the winter and all through the summer, actually. But so what's interesting about that is the whole plate solve problem, we had to do that we'd take photographs, and we would plate solve to figure out exactly where we were. But our photographs were taken on glass plates that had film emulsion on them. Okay, and the plate solving was done. Actually, the astronomer that I knew there was a guy named Lee Breakiron, a really cool guy, and he would do all that work to plate solve, and then I would take a lot of the pictures for doing our parallax studies, which is figure out the distance to stars like this and stuff. But you had to do it manually back then, and there was no concept of a go-to telescope where you could just, like we're doing tonight, go to this cluster, boom, it's there. So what we did was we kept charts, and as Daryl says we did, in the back here, it's still here. In the back room here, I have a Bonner Dirkmerstrung, which is a German atlas, which is a big atlas, and all it has is tiny black dots on it, like a negative, like you're looking at negative, but it's printed. And you would use a set of rulers which had, these reticles and guides on them, and you would measure the locations of the stars and use that to decide where you were going. And all the program stars were taken by doing those measurements and saying, okay, we're going to go to this star. What's the right ascension and declination? Well, based on what we see, this is it. And then we make a little finder chart, and boom, that's where we would go. All right. So, very cool.
I have more star charts. You can just take a...
Oh, yeah. I have my very first chart here. The very first one I ever had was called the Edmund Scientific Magnitude 5 Star Atlas. I've actually got...
That was my first one.
I got 5 of them here. Okay? And they're probably worth some money. But my next one was called the Scale Nate Pliso. And
I have that one too.
And I got the black and white one, and then I got the Wiltirian Atlas, which was a full color atlas of the night sky. And when I got that, everything changed because now I had color. Oh, was it beautiful?
Sky Atlas 2000?
Yes.
I have that one too.
Yeah. And then I got a book that had really cool stuff in it called Uranometria. I think that was Uranometria 2000. And that was a wonderful book. Then I got a catalog of all the NGC objects, but in finder chart form, which is really cool. And I got that not because I was going to use it. I got that because it was just such a beautiful thing to put on a coffee table, to be honest with you. All right, anyway, I'm sorry. I'm talking so much. Hedrick, Mike Hedrick has a question. Go ahead, Hedrick. Mike, sorry. We'll take some images of this, by the way, while we're here. This is the Jolly Roger cluster. Let's do a 25-second exposure of this to see all the members of the Jolly Roger cluster. Okay, and we'll stack this as well and get rid of the past stack if we have to, and we don't. If you were lost in the middle of nowhere, could you use a telescope alignment process to determine your location on Earth? Excellent question. Yes, you can, because wherever you are, if you look overhead, the star that's directly overhead is at your latitude. Okay? And so you could use that to determine, and the distance actually from the horizon to the North Star, if you can see it, is one that will be very valuable to you as well.
Wait, say that again. Say that whole thing again.
The star that's overhead, okay, the latitude of the star is directly overhead, okay, is going to be your, I say latitude, is going to be at your location on Earth, the declination of the star. So that'll be your latitude. So at your meridian, and I could probably show it on it.
Your latitude is the
distance from the horizon to the North Star.
North Star.
Yeah. Okay. And what I'm trying to show here, let me see if I can show it. That's 50. Okay. All right. But the declination of the star that's directly over your head will be your latitude as well. That's it's the opposite side of the 90-degree triangle.
If, say, you're at 40 degrees north latitude, the North Star will be 40 degrees above your northern horizon. Mm-hmm. And from there to the to the celestial equator is 90 degrees.
Yeah.
And that would be high in your southern sky. And then the rest of the way down to your southern horizon would be the 40, 90 take away the 40. And so if you're 40 degrees north, your southern horizon is 50 degrees south.
Your horizon, yes.
Yeah.
Yep. This is beautiful. Look at that. Oh, we got something here, Daryl. Look at that. Didn't even know that was there.
What?
There seems to be some kind of a nebula here. Let's see what... I only did a 25-second exposure. It doesn't surprise me, though. Yeah, see, there's something here. I could be wrong.
Hedrick, that question was sort of posed in an old Robert Heinlein novel. I can't even think of the name of the novel now, but they were dropped on a planet, and they had to figure out where they were, and they did it by looking at the sky and how high the sun was, what direction the sun rose, so you knew where east was, etc., etc.
Yeah.
It was one of Heinlein's older novels. I can't even think of the name of it now.
I don't remember the name. See this, even a simple cluster, guys, looks beautiful when presented in the right light, right? And this is just beautiful.
I don't see a skull. I don't see a Jolly Roger, but...
Well, I agree. I'm not sure. This has to probably do with this shape right here. I'm not sure where.
That dome shape? Semicircle?
Yeah, that might have something to do with it.
Top of the skull, yeah.
Might be something to do with it, and this might be an eyeball here. Eyeballs or whatever.
Oh, that could be.
I don't know. Doesn't look bad, though, I have to say. I want to thank all of you for coming out tonight, too. We're going to have some fun tonight. We're still going. There, I've color corrected now, so now you see it like it should.
Izabela would like to look at the Wizard Nebula.
Alrighty, that's a request from the chat, and we will do it. The Wizard looks beautiful. Tonight might be a really pretty one. It's nearby, too. So let's get to 10 stack. We'll do 11. And I'm going to change this name here to the Jolly Roger because it's worth taking an image of. And it'll be cluster, so I don't have to say open cluster. You know it is. Okay, so we've stacked 11 images here. The Jolly Roger is really pretty. Okay. Actually, let's take the 12th in. It's almost here. Okay, we've done 12. And now we'll save it. And then save it exactly as seen. There we go. And we'll clear it. But don't worry, it'll be back. Alright, and now we'll go into our night vision mode, which is really works so well for us. There's night vision mode. And alright, we'll back out here. Whoops, too far.
Dean, I think I see the two stars you're talking about.
These guys right here?
Yeah. We don't know if it's a true binary or if it's just an optical double.
Yeah.
Optical double is just two stars along the same line of sight.
Yeah.
They're not physically associated.
You have one here and one here, so they look like they're associated with each other. You see 2 points of light near each other.
Yeah. If it's a true binary, they're orbiting each other.
Yeah. And that we could see in its spectrum by looking at the spectral lines in its spectrum. We could detect the motion of the stars going around each other because the lines will be red or blue shifted depending if the stars are orbiting like this, as the stars coming toward us, the lines will be blue shifted. As it goes away from us, they'll be red shifted. So you'll see the lines in the spectrum moving left and right.
And in the old days, they used to look at stars over the course of time and plot if they had moved, and
yeah,
they could eventually, derive an ellipse of their orbits.
And that was called astrometry when they measured positions of stars directly. And that was the most error-prone method for doing star measurements ever. It was never, ever correct usually. And it just gave sort of a... you could say things like, okay, these stars may be orbiting each other. You couldn't definitively say it. So, but that's how that worked.
If they watched it long enough, they could. If they could draw a complete ellipse, that meant something was orbiting something.
Well, name a star that you could watch the complete orbit of.
Well, don't put that on me. I don't know. It depends.
Well,
I know
don't have any.
Well, sure there are.
No, there's no stars that orbit each other so quickly that people can make a determination over like 2 years, whatever.
Sagittarius A.
We can't see that in the 1800s or the 1700s.
All right. I mean, you're moving the bases here.
I wasn't, but I know what you're saying. Okay, we're doing the wizard now, Daryl. So.
All right.
Okay, so we'll do the wizard. This is for Izabela.
Hedrick,
What's the wizard's NGC? Okay, gotta look that up. It doesn't know it as Wizard Nebula.
Give me just a second.
Okay, it should though. Why doesn't it know that? It should know the wizard.
NGC 7380.
Okay.
Hedrick, if I get your question, is the motion of these stars recorded online somewhere? They have a good handle nowadays on the motions of stars in the sky. They're getting more all the time with all the satellites, I guess Gaia and Hipparchus and stuff like that nowadays. They have a good handle on how stars are moving in the sky over the course of time.
Yeah.
Like Barnard's star, for example. That's the one that is moving really fast across our sky. But they have a good handle on stellar motions.
Okay, I'm going to get to Izabela's question too. I wanted to add though, one of the things we see, there's the wizard. One of the things we see when we look at stellar motions, and you say, well, how do you figure them out? Well, you can very precisely measure the positions of stars these days in the sky relative to other stars. But you have to keep in mind that in order to determine the speed of the star and which way it's going, the velocity vector, that's called its proper motion, measured in arc seconds per year in the sky. To do that, you have to do a couple things. You have to first understand the motions of all the other stars nearby, and figure it out from what's called a local standard of rest so that you can actually determine what the star is actually doing. Because if you see a star move to the left of another star, how do you know it's not that other star that's moving to the right?
Yeah.
So we've got that confusion too. Everything's moving in the universe. So there are uncertainties on every single velocity vector for a star. There's no specific one that says, okay, this is moving at 12 arc seconds per year, or 12 arc seconds per millennium even. I mean, so we don't have that. But we do have uncertainties. There are always a plus or minus 2 or 3 arc seconds per year, whatever. So it's pretty interesting how this all works.
Yeah, and techniques have changed with modern technology.
Yeah.
As I said, I guess you'd probably remember the names of the satellites better than me, Mark, but I think the Hipparchus, the Gaia, that has been plotting, stars in the sky.
Yeah.
They're getting it down to quite a science now.
Yeah.
And beyond proper motions and stuff like that, Hedrick, how the stars are actually moving in the sky. I mentioned that they redo star atlases every epoch, I think they call it, to update star positions in the sky.
Yep.
Beyond stellar motions themselves, the whole sky itself is slowly shifting due to precession of the equinoxes.
Yeah.
So the positions of all the stars are slowly changing over time just due to Earth's axis wobbling every 26,000 years.
Yeah.
It is a notable effect over, a period of time that they have moved, and so they update the star atlases. Somebody mentioned earlier they got a copy of the Star Atlas 2000 back in the 1980s. Well, that was star positions for the year 2000, and they will probably update that Star Atlas 2000 in 2050, if not beforehand. I forget how often they update them.
Well, if you look here, okay, if you can even read this, the right ascension and declination, these coordinates, which are the extension, the right ascension is the extension of the longitude lines out into space, and it goes 24 hours instead of degrees. And the declination is the up and down, plus 90 to the assessed equator and minus 90 to the South Pole. If you notice, there's in parentheses here, it gives you the right ascension and declination, and it says J2000 on it. And that's the coordinates from the epoch, EPOCH, 2000. But then the right ascension and declination on date, meaning projected for today, is this value. And that on date value is the one that we subscribe to and we always look at. So right now we're pulling the Wizard Nebula in here, and that's going to look really pretty. And I just got to make sure I get it in the center, and then we can just do an alignment on it. Hey, that's pretty close. That looks good. So I can come back here and say for the Wizard Nebula now, we're going to tell the telescope to align there, and you'll see this move over. Boom. That's centered. All right. So now we are all aligned, and then I can get rid of these guys here. All right. So let's do dare to try. Now that we're stable and going over here, you can see us moving with stability here, guiding. We're going to do a 40-second shot of this guy. All right, off it goes.
You won't have to worry about the moon until about midnight tonight.
Right. That's why I'm trying to put stuff in here. It's going to look good. Okay, now we're going to go pull this up. Let me move this guy back to there. And
the moon is at third quarter today. So a third quarter by definition rises at midnight.
Mm-hmm. All right, so we are about to, we have 7 seconds, so I'm going to take this off so we won't get it blasted out. And now let's see the Wizard Nebula. Look at that. That is really pretty. There's some dark nebula up here, too, that might come out of this as well. Look at that little line right there, Daryl.
Yeah. Oh, that may be the spider legs that got me started on all that. I forget.
It might be.
The dark lines, the one you pointed out, there's a bunch of them to the upper left.
Yeah. Right there.
Very distinct looking.
Right there. Yeah.
Or upper right, I mean.
Well, but on the upper left, look. You got them there. You got them there.
Yeah.
You got some up here, right there. You got one right there.
That's the one I was talking about.
Okay. Okay, let's just zoom in here just to see how our stars look. Our stars look absolutely beautiful. Look at this little tiny pair right here. 1, 2. See those little two? 1, 2. This is excellent. You see the noise level here. I mean, we've stacked 2 images. The more we stack, this noise goes away because it's random. All right. Only stuff with data in it, like a dark nebula or an emission nebula or a reflection nebula, those things will come to the top. Because remember, we're stacking successive images on top of each other to make a stack sandwich, a photo sandwich, image sandwich, if you will. And so more of this dark stuff is going to go, more of this noise is going to go away.
I'm curious to see if this is going to resolve tonight.
See the wizard here and the
to
arms.
see the figure of the wizard, and then I always see that
girl.
little girl over on the right. Yeah.
We'll find out.
It's like he's holding his arms out toward her, and she's holding her arms up toward him.
Yeah. That's Daryl's version of it. That's not, I don't think, what they actually thought, right?
Yeah, that's what I see.
Mm-hmm.
I mean, it's a wizard. He's got a hat on and a tall hat, and he's wearing his wizard robes.
Yep.
Both his arms are bent, pointing to the right, and maybe his knee or his legs down below. And then there's a little figure over in the mid right. It may need more zoom, or you may need to see a different image of it. That it looks like a little girl standing facing the wizard, and her arms are raised toward him with her hands together.
Yeah. I want to ask. I want to answer Mike Hedrick's question. Mike asks, Mark, how far does the entire solar system travel through space in one Earth year? That's actually a really good question, because it really puts it into perspective. And the answer to that question is actually pretty simple, believe it or not. We've measured this based on our local standard of rest and comparison to the galactic center. We're actually moving at about 230 kilometers per second around the center of the galaxy. All right. And that means about 7.2 billion kilometers per year. All right. So that's a pretty good motion, and that's that is our speed and distance that we move. And in terms of direction, we're actually moving pretty much in the galactic plane, but there is an oscillation that may occur in our motion that we haven't well, we've actually tracked up and down motion. There's based on I'm disappearing here. Help me, I'm vanishing. Here we go. Based on what we see in our motions, we might have an up and down oscillation going on as well. We see stars do that because a galactic disk is actually several thousand light years thick, and we're kind of in the galactic disk. So I hope that helps. I want to say hi to Bullwinkle. I want to say hi to Jane Murdoch. Jane's been here. I don't think she was here for the Mars party. I'm not sure. We had a Mars party in the front lawn, and right after everybody left, I saw those beautiful, those stunning iridium flasher satellites, 2 in a row, and they gave me a double shadow on the ground. They were so bright. It's a glare from the sun shining off these bright panels on those satellites at the time, and as it went over our particular location, the glare was hitting us. You can calculate it. You can look for it and literally gauge your night around it if you wanted to. But they've stopped using that constellation. I think they've deorbited a lot of those into the
iridiums, yes,
into the great satellite graveyard of the Indian Ocean and out in the Pacific.
Yeah, the earlier generation of iridiums, they've been taken over by the newer versions, and the newer versions don't cause the flares like the old ones did.
Yeah.
Well, those things were tremendously bright. Sometimes.
We can see your wizard now, by the way. You see it?
I see it.
Yep, it's there. Let's give ourselves just a little bit more of a proper wizard look here.
Excuse me.
Yeah.
Continuing what you said a minute ago, the direction we're moving in space as we rotate around the galaxy presently is we're headed roughly toward the star Vega. Actually, it's somewhere in Hercules, a little bit over to the west of Vega.
Yeah.
But as a general thing, if you look up in the sky, we're headed sort of in the direction of the star Vega.
Mm-hmm. And Vega is approximately in the galactic disk, and we're heading toward that. And we, again, because of long-term perturbations to our orbit around the galaxy, our sun is going to go up and down probably cyclically. We don't know exactly how it may have in the past, but we only know what it's doing now. So we see that.
Yeah.
Let's let's move this out of the way. And why don't let's get rid of this for a minute. All right.
And beyond our motion in local space, our whole galaxy is moving in the general direction of the Virgo cluster, which is a springtime thing. And
there's another complication there too, isn't there?
Then the Virgo cluster, and us with it, is heading toward the Great Attractor, which is down in the constellation Norma.
And let's add another complexity to that too, and that is that our Milky Way, locally, if you want to consider it local, is also moving in the direction, along with the Andromeda Galaxy, toward each other. So, whereas it's all moving toward the Great Attractor, the galaxy itself and the Andromeda Galaxy are closing the distance between each other. Okay? The Andromeda Galaxy has a lot more mass than us, so it's affecting us more than we're affecting it. But that means that we are also accelerating toward, or moving at some velocity toward, the Andromeda Galaxy as well. And meanwhile, we're all moving in the general direction of the Virgo cluster and toward the Great Attractor. So we're all going this way, and we're doing this with the Andromeda Galaxy and then going this way, and that's why we need to have what's called a local standard of rest, a point where nothing is moving that we could use as a reference on which to gauge everything else. Yeah. Hey Ray Cosmic Ray is with us. Thanks for coming along, Ray. Ray, I saw in the comments last time that you were a little concerned we were going through Cygnus. Let me know why. Because riding up the summer Milky Way for one last run was, I think, a pretty good idea. Let me know what your thoughts were. Okay, we've stacked 14 of these now. Let's zoom in on this now. Okay, this is the Wizard Nebula that we have brought up for Izabela. Let's see if we can add a little to it. This is going to help us see more of what's in it. Okay, as you can see when we pull out of this area, there's a lot going on here. Does it strike any of you as amazing that there's this many stars in the universe? How many worlds do you think you're looking at here like the Earth? Maybe none. Maybe a lot. As I said, the dark nebula is where it's at. It's in here where new stars are being formed and new planets will be born. But you might have stars out here that are forming their own planets. So
I'm gonna post something in chat.
Okay.
This is an image of the Wizard Nebula at the Wiki article. Open that if you like, and once you see the image, hover your mouse over it and click the image until it's as big as it can get, and tell me you don't see the little girl on the right side holding her hands up in the general direction of the wizard. He's sort of reaching out toward her.
This is his arm, one of his arms. I think this is the other arm. And you're saying this is the little girl right here?
Yep.
And it's one of her arms?
Yep.
Yeah. Well, we can see it right here. That's pretty interesting.
Isn't that cool, Bonnie?
Now, when you ask about double stars, guys, well, I guess you could say, well, are these two guys double stars? How about these two? How about these two? How about those two? How about those two? You know, everywhere you look, you can see stars that could possibly be double stars, you know, orbiting each other. But in most cases, they are actually in line of sight. Simon asks what you've been drinking, Daryl.
Yeah, I saw that. I am drinking a cup of green tea.
Let's pull back
In fact,
the
it's
telescope.
8:30. I should be putting it down.
There we go.
Some people simply have no imagination.
Or some people just have a sense of humor.
Yeah?
Yeah. I thought that was funny what Simon asked.
Okay.
All right. Okay, so we are at 19. We're going to go to 20 on this, and then we're going to save it for Izabela. And for any of you who would like to see it, this is the Wizard Nebula. Okay.
And I just made a major admission in chat. I had a short brandy before dinner.
Well, how about that? Let's just fling that right out there now.
Well, he asked what I'd been drinking, so I told him.
There you go. All right. We are set. So we're going to pause this now with 20 stacked. And we're going to save the Wizard Nebula. And it'll be in a directory called the Wizard Nebula out there. Or Wizard Nebula. All right. We'll save exactly as seen. And we're going to clear this.
This is one we should come back to when we have more focal lengths. I bet we can see the little girl here.
Well, we can see it here now already. But yes. Pull that out. All right. Ray, did you answer what I asked about the Cygnus thing? I didn't check. That was a question for Cosmic Ray. Drop a deuce too. How you doing? Actually, Drop a deuce says something interesting. Planets are more plentiful than stars? Question mark. Yes, they are. So all the stars we saw in that last image, there's more planets in that image than there were stars, in all likelihood.
Yeah.
Oh, okay. Cosmic Ray says, just got tired of 4,000 mosaics of the dark stuff in Cygnus, but can't have enough mosaics of the Veil Nebula. Okay. That's in Cygnus. All right, Ray. I got you. But you have to understand that, these mosaics really show us what's going on in our galaxy. And as wide angle as we are, we're at just the size where we can actually zoom in quite a lot and be able to see stuff. But we're not wide. We're not so far out wide that when we zoom in, everything gets fuzzy. Okay, so we're at a perfect focal length in order to do these mosaics. To be honest, so I'm thinking we'll probably continue to do some of those. And, folks, you can weigh into, of course. I don't want to make anybody feel that we do too much of one thing. I want to say hi to Astro87, who's here. How you doing? Why do you call yourself Astro87? Tell me you went to school for astronomy and graduated in 1987. Just tell me. I want to know. Cosmic Ray says, yes, I've been posting a lot in the chat trying to correct you guys. Okay. All right. Okay, let's zoom back out. Here we go. Okay, there we go. And I'll do that. And now let's go check out another one of my absolute favorite objects here. Okay.
Cyclone, I could ask Mark if you like. If you don't like my answer, I dare say I could say it in less words than Mark can.
Wait a minute.
The Earth's pole is wobbling over the course of time. It's just like if you take an old-fashioned top and spin it as that top starts slowing down, instead of standing straight up, the top is going to lean over and it's going to start walking in a circle. And that axis of rotation is called precession. Now, Earth's axis is doing that. It takes 26,000 years for that precession to make one complete circle.
Yep.
And as that circle happens over the course of 26,000 years, the direction Earth's axis is pointing shifts, and therefore various stars along the course of that circle will, in their course of time, become Earth's North Pole star. Right now it's a star Polaris. In the future, Vega could be one of the stars. I forget exactly. I believe Deneb is also on that circle. There's a lot of bright stars along that circle, and each, over the course of 26,000 years, is going to have their turn as the North Pole star. This is called precession of the equinoxes. And it's causing all the stars in the sky to slowly shift from, when the dates of the equinoxes happened, it has been shifting to the west, I guess, yeah.
Well, very good. Now you need to answer Mike Hedrick's question. Do it now.
Balancing an egg?
Yes.
I've heard both ways. I've heard yes, I've heard no. I've never done it myself, so I can't really say.
All right. Astro87 answered my question. He says, I'm a beginner. Astro was the first thing to come to my head. Awesome, brother. That's very cool. All right. This should be the Lobster Claw Nebula. I'm not sure. I thought the Lobster Claw Nebula was something a little bigger than this, and I thought it was near the bubble, and it is. So, okay. So this is a rather extensive nebula. So I think I see some of it here. So we're gonna move this way just a little, because this nebula is really extensive and beautiful. So we'll check this out too, and we'll make this a 35-second exposure. Let's wait for us get our guide star. You can watch up there. Okay, we're calibrated, and now it's guiding. We'll let it stabilize, and then head into our 35 seconds. Here we go. And there we are. Temperature out there is 11 degrees Celsius in the building. All right. This will be a 35-second exposure. I've done this. We'll be wait it out for this. Okay, what do we got? Yeah, look at that, huh? We got it. There, we got the whole lobster claw in here. So let's remove that guy, and let's do some shots here and some color balancing. All right, and we'll move this down. I'm gonna go to my zoom mode here, so I can more adjust the curves easier. I'm gonna pull this off the main curve. This is our data here that you see down here. This is the data that the camera brings in, and you have the red, green, and blue curves that are aligned with each other, which is good, right? And this is the black level. So if I pull this in, you'll see that it gets darker and darker and darker. And this is the data from the nebula right here. So as I move to the right, you'll see the nebula disappear, all right, until we have just stars. I move back to the left, and we get more of the data, because this yellow curve is what's intercepting the data right here. So as I pull it to the left, you'll see that we end up with more of the data from here, right? And now this right here, this is our mid-level, And if I move this over, you'll see that we're intercepting more of the curve, and it should get brighter now. All right. Okay, and then when I move these two together, when I move the black toward this mid-level, we're doing something called pushing the exposure, pushing our system. And you'll notice that it gets brighter, but it also has a negative effect. Faint stuff might get lost. But again, look at the stars. Look at all those stars.
I don't see a lobster claw.
Oh, you don't? There it is, right there.
I see a catcher's mitt.
Oh man, don't fill my head with new things. That's not a catcher's mitt. Yeah, it's a variety of things, obviously, that we see when we look at these. You can make up almost anything you like. Here, let's take the telescope out for a minute. All right, and check it out. Once our Starlink reacquires. That's better. And then fill it.
In fact, that's a left-handed catcher's mitt.
Well, I guess that could be true. Where's the thumb? Here? No.
They're on the left.
This guy?
Yes.
Yeah, okay. All right. Well, that could be a first baseman's glove. How do you know it's that? And here's the ball? Beautiful.
It depends on if the palm of the hand is facing us or away from us.
Oh, yeah.
I'm left-handed. I'm prejudiced, so it's
Well,
a left. You don't see many left-handed catcher's mitts anyway.
Well, I catch with my right hand. I write with my left hand. I kind of do many things different ways, I guess. So this is a lobster claw. This is beautiful. We've only stacked 6 right now. But it's not bad, huh? That's a really pretty little nebula.
Is this still in Cepheus?
I have to go look at the constellation borders. Let's see.
I remember this though. I remember those.
It's near the bubble.
Okay.
We did a mosaic, remember? And we included the lobster claw in the bubble.
Yeah, I remember the little bright line of stars up at the upper right.
Okay. That's the dormouse cluster you're talking about, I think. This is the dormouse cluster.
Yeah, that's very distinctive.
Yeah. Okay, so let's see now. As we look at this. Are we in there or are we in Cassiopeia? Are you sure?
Californieto.
Yeah, the Californieto. Yeah, it's in Cassiopeia. It's not in...
Okay, well, close.
Close. Yep. All right, let's just back out of this for a bit, just so you can capture the whole thing in one shot. There we go. Look at that.
Cyclone says it looks like a crown broken into pieces.
I guess it does. Yes, it's the crown jewels, see? And the diamonds are flying off. Not bad.
That little star cluster, that's amazing.
Yeah. Let's see, there's another one too, so let's zoom in on this. And let's check out where we're actually... It's going to be at the top. If you know what the writing here is upside down. We have the dormouse cluster up there. Yeah, and that's this guy right here.
Robin Curtis said she sees the cave is right there too.
That's true. See, the dormouse cluster looks like this. And that's
Okay.
what you see when we look at that other... Yeah, I'll come back out of this. Hi, Robin. Nice to see you. Okay. There's the cave here, yeah. Have we looked at IC10? I don't remember looking at IC10.
Maybe we should.
Yeah. It's kind of small.
Yeah.
That's all right. Here we are. Okay. I'm just whipping around the pole here. Let me get rid of my zenith lines here. Azimuth lines. Don't need them. Okay, so we have the Little Rosette Nebula down here, which I wanted to check out as well. So that nebula right there is Sharpless 2170. Don't forget that one. We're going to go to Sharpless 2170 shortly. And that'll be this one here. Yes, the Lobster. Alright, maybe we can do the Cave Robin. We'll see. Robin Curtis, otherwise known as Database Girl. DB Girl.
When you look at this, this reminds me of what we were saying earlier about the Lion Nebula you mentioned.
Yeah.
You see the red in one area and the green in another area.
Yeah. I wonder if that's actually the correct color or if that's actually a reflection nebula. I know that sometimes the sensors pick up colors incorrectly, but I have to look and see. Color correction shows it to be green, which is very interesting.
You know, which usually signifies oxygen 3.
Yes, it does. Doubly ionized oxygen, yep.
Cindy Murphy, I think, sees a bumblebee.
Oh, I see it too. This is the head, this is the body, and these are the wings, Cindy? Is that what you're talking about?
I could see that, sure.
Then she'll tell us, no, that's not at all what I see. It's anyone's guess, Cindy. Anyone's guess. Cyclone's asking what time are we guys live streaming tomorrow. I'm going to see if I can set up a system to do that from here with a regular camera. I do have my USB connection to the camera. I just have to get it here and build a new broadcast source for it, basically, if I can get it to work. And if I can do that, we'll stream the Leonid meteor shower. But that's going to be taking me much of the day tomorrow to figure that out.
And that's if the weather cooperates.
Well, it just has to be light clouds. Let me see what tomorrow's weather's going to be.
Bill will probably stream it too, since he
will.
does meteor showers.
Yeah.
It's supposed to be snowing here tomorrow night.
Well, that's Colorado. You get snow 100 days a year. No, I'm just kidding.
Well, down here not so much usually, but it's
Yeah.
actually we're behind a lot of the rest of the state. We finally just got a little snow on the ground a couple of days ago.
Yeah.
Denver's gotten a lot more than we do. They generally do north of the Palmer Divide. But it's supposed to snow tomorrow night, and it's supposed to get down into single digits too, from Thursday into Saturday.
Wow. That's pretty cold.
Feels more like January than it does November.
Well, I did fire up the wood stove today and had it running all day, and the pellet stove at the other end of the house. And it kept the whole house at around 72. I didn't have to use the propane tank. I have a 500-gallon propane tank underground outside that I use for heating sometimes. So, you know. Simon Thompson says it's been many a year since I've seen snow. You know what that means? He lives in a warm climate. Bullwinkle.
Parts of Australia do get snow, don't they, Simon?
Yeah, I'm sure that you might get snow down toward
Blue Mountains,
Melbourne, maybe. Because winter down there, they're at the opposite latitude of where we are, and we get snow, so I would think they probably get snow. Izabela's having a cold rain right now. Well, that's so exciting. Not. Sorry to hear that. All right, I was actually going to check the weather out and see what I'm going to get for tomorrow. See what
I think that dormouse cluster looks really cool. Looks almost like 2 straight lines of stars. I wish I had a wood stove. I'd settle for a fireplace. It's one thing I missed when I lived in the high country.
Having a wood stove?
That or a fireplace.
Okay. The other thing, too, keep in mind is moving forward, we're going to try and set up wide-angle cameras in the observatory. Like, for the Leonid shower, we're going to do the all-sky camera out in Arizona, even though we don't expect to see Leonids too much, but we might. And so, knowing that, we're going to run the camera all night. I'm not sure if we'll stream that like we did the other night, but we might. Okay, what's our 10-day forecast? Okay, so tomorrow, being Thursday, it's late tonight into Thursday, and then Thursday night into Friday. Mostly clear in the evening and becoming partly cloudy tomorrow night. But no precipitation. Wednesday night's going to be cloudy here, which is tonight. So, can't do it tonight. Okay, we've got 23 stacked. Oh, look at that. This nebula actually has a very real modeling right here, which is kind of interesting. Let me zoom in on it. See how modeled this looks? That's real. It's like a pillow. It's really interesting how that looks.
I would wonder, again, if this might be the case. Might the bright red star down toward the lower part of the nebula be what's lighting up the red part, and then there's some brighter stars up in that upper part close to that green band?
Well, it depends what kind of red star this is. If it's a supergiant, it's not going to have the ability to ionize a massive nebula. Only the O and B stars can do that, and those are blue. Red stars are always, say around 4,000 Kelvin and less in temperature.
Yeah.
You're not going to have anything brighter, so I don't think there's a lot of UV coming from this, and I don't think that's what's doing it. This is probably a foreground or background supergiant or a star. The star that's doing this could be this guy right here.
Okay.
That's potentially possible. Again, everything's in 3D, so you don't know where all these stars lie relative to this. You might say, oh, well, you got to go past all these stars to get to here. Not necessarily.
Does Stellarium describe this as a emission nebula?
Well, it better, because that's what it is. It's an H2 region, yes. It's an emission nebula. Doesn't tell you what's actually causing it to glow. That you can get from the SEDS database, SEDS, and from other information online about the Lobster Cloud Nebula. Simon's in Perth, okay. Hey, Donald Kunzer, how's it going? That's the thing. Donald Kunzer says, 2 hours you've been going. I keep missing the alerts. I have to tell you, when you get into YouTube, make sure that when you click the bell, it's a drop-down box. Drop down the box and click all notifications. That may help. I don't know, man. This is problematic. I don't know why the alerts aren't coming through. I've got other people saying they're not getting alerted either, and that really bothers me. Because you miss a great deal of what we did. Obviously, you can see it in the replay. And that bears fruit when you actually watch who's looking at our streams. You find that by the next day, there's hundreds of more hits than there were the previous night. So clearly, it's the post broadcast that's getting all the attention, I guess. Okay, so we're almost done here with this one. Yeah. Now what I do when I process this, I'm gonna take all these stars out and just process the nebula, and that allows us to get better a better look. Go ahead, Daryl. You were saying.
Cyclone wants me to ask you to look at Polaris. I seem to remember asking you that before.
Okay. Well, we can try it. I mean, we can certainly look at it. Obviously, the telescope can point to it. But it'd be interesting because I've not pointed the telescope at Polaris since I aligned it. Okay.
Well, Polaris is okay to look. It's a double star.
Yeah.
A lot of people don't know that. It's a pretty double star.
Okay.
That's about it.
Okay, we're pausing this and saving the lobster claw with 30 stacked images. And we'll save it exactly as seen. And then we'll clear it and go back to our preset setup with the night vision system mode. Whoops, I gotta get rid of the stack. I thought I did. Okay.
I don't know if your focal length will split Polaris if we wanted to see the double star.
It's a good question. Well, we're actually not that truly that far away.
I thought I asked you about looking at Polaris once, and
You did.
you thought it would interfere with the cable management or something.
I did, but we can try it now because I've messed with the cable management fairly significantly. So now we're gonna try it. If you look at the telescope, you see it's leaning way over, and it's gonna go right out there to Polaris. It should put Polaris right in here. There it is. As you can see, we got circles, because we're actually really, really close to it. Let's get our telescope back here. All right. Alrighty, and now it also messes things up when you try to move in different directions, a little bit.
Yeah. Well, I suspect you're describing the corollary problem with trying to point an Altaz telescope straight up.
Exactly.
The motions become infinite.
Yeah. So now, if we try to move the telescope now, we go west, watch what happens. It's going to go in a direction you don't expect it to.
Yeah. Takes a whole lot of movement to get
a little distance.
Telescope to move a small distance.
That's right. That's right.
Rotational movement.
That's right.
Izabela asked, let me find that.
Well, this is where we'll stop it there for that. Let's
She retracted the message.
Oh, she did?
Oh, there it is. Marc, what do you think about the search for Dyson spheres, ET megastructures, and industrial pollution like what SETI does?
Oh, yeah. Well, to be honest, Dyson spheres may or may not exist. They may or may not exist.
Well, I remember some speculation back when, what was it, Tabby's star?
Yes.
That's
right.
Excess infrared signature or something.
That's right.
Some people speculated that we were seeing a Dyson sphere under construction or something of the sort.
That's right. Polaris wasn't too exciting, and so we're going to try to go to the Iris Nebula now, which is more exciting.
And she also said, and industrial pollution, like what SETI does.
Oh, yeah.
This might get into the thing like you talked about, what I think it was Carl Sagan suggested, looking for certain signatures on exoplanets and stuff.
Yes, in the atmospheres, you look for pollutants in the atmosphere that are significant, that would be, for instance, indicative of an industrial revolution, and so forth.
Yeah. Excuse me a moment, please.
All right.
Right back.
Okay. Okay, we're going to move south a little bit now and move this up. This is the Iris Nebula that we're looking at here. And the Iris Nebula is a beautiful nebula. It's a dark nebula where a star formed inside the dark nebula, just like I talk about. And that star has starlight has gone out, and the dust cloud of this nebula is illuminated by it. And in effect, what's happened is the dust particles are scattering the blue light from the star. Now, there's undoubtedly hydrogen gas in this region, and so you might say, well, then how come we don't see hydrogen ionization? It could just be that there's not enough hydrogen to show. There's probably a soft glow throughout the area, but we don't see it readily right now. But I'm going to take this picture here once we get in there, once we finish searching. Okay, you got my starry backdrop behind me. That's actually the desktop for this computer that this is all on out in the observatory building. Okay, we're doing our guiding. Let me watch what it's doing. Okay, we're doing fine there. Let me just do one little check here. All right, so let's now go from why it's 2 seconds is a mystery to me. Let's do 40-second exposure here of this now that we're guiding fine, and then we'll head into the target stack area, and we're gonna clear this. All right, and now we're ready. And if you follow that progress bar over there, ding 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 ding, oh good, more stupid stuff. And it seems like once a night things like that happen, don't they? I'm gonna hide the user from this channel, so that's the end of you. Hi there, Michael Klagas. How you doing? He's shooting the California Nebula right now. Fantastic. Okay, now if you notice, this is the view where we haven't adjusted our settings yet. If you notice, the dark is set all way over here off the curve, so that's going to be really, really light. But if we move it all this way, okay, and then move, let me just actually have it do it, and then we can put it together. There we go. So now you can see this beautiful nebula with this cloud behind it. And there's another one over here that's going to materialize over time here. And you'll see much of this noise go away in just a second here. Watch. Ready? There you go. So now you see it's even more resolved. Now that thing is immediately showing up. So to help even more, let's color correct. There you go. And now you can see very well. This stuff is actually brown, which is indicator of is an indicator that it's actually like a silicate dust with carbon. And when we say dust, we don't mean dust like you see in sunlight. That's hugely dense compared to what you see. If you look in sunbeams coming in, you might see dust floating through here and there. These nebulae are even more sparse than that in terms of the amount of dust. Now, like you clap an eraser in the dust, it's like, whoa, that's like a huge amount of dust. That's way too dense for these nebulae. We're talking about just a few atoms per cubic centimeter, okay? not even particles yet. I mean, a few atoms per cubic centimeter of these little tiny within this area, and the dust is made of these micron-sized particles, and the gas is extremely sparse. As I said, a few atoms per cubic centimeter. I mean, that's it. Okay, that's it right there. A few atoms in a little space the size of a cubic centimeter of the gas. So it's pretty interesting how these nebulae work. Now, one thing we can look at right off the bat is over here, as we zoom into this part. Okay, look at this little window. We're seeing through the dark nebula to the stars beyond out here. That's the other side. Peekaboo, right through a little window. Isn't that cool? Okay, and this star's dust, the dust particles around the star are scattering the blue light of the star, which is the high energy light. Now, I've talked about this before. This is the same reason that we have a blue sky. It's the same type of scattering process. It's just with dust particles in space, not dust particles in the atmosphere or atoms in our atmosphere. Atoms of nitrogen and diatomic oxygen molecules. So, because those do the scattering as well. And that's called Rayleigh scattering, the scattering that gives you the blue sky. But if you think about it, you think, well, wait, why do clouds look white? How come clouds aren't blue? Yeah, see, that's actually a very interesting question, because clouds are white because it's a different type of scattering going on, because we're looking at different atoms, compounds, that are scattering the light. In water vapor clouds, H2O vapor, what they do is they absorb all the light and emit all the light in all directions. So you don't get a selective color being emitted. You get all the color emitted of the sun, and so the clouds look white. But with Rayleigh scattering, only that blue light, the high frequency light, is absorbed and re-emitted in all directions. So no matter where you look in our sky, you always see blue. Well, same with the nebula. So there. This is pretty, Daryl.
Yes, it is.
And there's a lot more tendrils that are going to show up and start showing up. You can definitely see the brown color set against the black. We can actually help that a little bit. Let's try this. Maybe like this. And pull this in. See how much we can do before we start to lose the contrast. Alright, that's actually better than I thought. So you can see this brown dust. Just so you get it, this brown dust is literally throughout this entire image. This entire image has brown dust in it. There's only a very few parts that don't, like right in that window. Right over here. Okay? A little window right here. All right, you see how almost everywhere you look, you're seeing brown dust of varying densities. Hey there, Michael Galea. How are you? Nice to see you. Cosmic Ray says this dust has to have light absorbing qualities to blank light out. There are very thin films that absorb light. That's very true, but this dust is actually not very dense at all. There's just a lot of it. I mean, if you have a full light year of depth to very sparse nebulae, that amounts to a very dense nebula as seen from our perspective. From within the cloud, you might not even know you're in a cloud. But once you're out of it, that density will be increased based on the fact that you're looking at a light year's depth of very sparsely placed atoms.
Yeah,
so,
we talked about this before.
Yeah.
Like you said the other night, you might have 30 or 50 atoms per cubic centimeter, and
at the most, yeah.
that's not very much in the big scheme of things. And
No.
looking across a centimeter, you're never going to see it. But if you stack up about a light year's worth of those centimeters, and all of a sudden it gets dark.
Oh yeah, yeah, that's true. And one of the things too is if you look at, for instance, and again, you need a good comparison. And let's look at, for instance, okay, let's suppose you have a little quantity of air. Okay, you're talking about a amount of atoms, say, just okay, we can say in mass, I guess, in terms of grams of air. Okay, you basically, well, okay, I'll do it in volume because we're talking about volume. Cubic centimeter of air, okay, has 90 million atoms. Okay, and that's a cubic centimeter of air, which you can't even see. Okay, with a dark nebula like this, they're going to have between 10 and 50 atoms in a cubic centimeter. Whole atoms in a cubic centimeter. So the difference in density is astronomical. Okay, astronomical. So when you talk about this in terms of, how they block the starlight out, it's because the size of the cloud is also astronomical. And that's what we're talking about here. So hopefully that makes sense. All right, so hey, we've stacked 13 of these so far. Now, as promised, this one's coming out nicely here. We're starting to see a tendril here that's pretty obvious. Go ahead, Daryl, you were saying.
Have we looked at the void yet?
This one, yes. Well, we're going to zoom in here in just a second again. I just want to... well, first, actually, let's take a look at what we actually have here. This histogram over there, right here, this will allow us to basically do a quick shot of everything that's in here. Okay, now you can see, look at this. Now you can see this out here and in there. Look at it, it's all throughout this image. All right, there's only a few places where it's not here, and you see some very dense areas that are actually probably more like, who knows, 40 to 50 atoms per cubic centimeter. But for a good portion of a light year or more, and that will tend to make things look opaque from a long distance away. This is pretty. But you see we have a lot of noise in this image because we're actually really pushing things. If we were to take this and go down this way, we'd remove some of the noise. There we go. All right, now that's pretty agreeable. That's more nice. All right, so now, as promised, let's zoom in on this void over here, which is actually a true hole in the nebula that we're actually peeking through. Check that out.
Lewis Ta asks, is that blue star a Wolf Rayet?
Actually, I don't think so. A Wolf Rayet star... a Wolf Rayet star is a very different animal. And this is just dark dust. And this is dark dust being illuminated. That is to say, it's scattering the blue light from the star. So this is what would be called a reflection nebula. And Wolf Rayet stars don't, especially this close embedded inside, don't actually generally create a reflection nebula at all. They'll create an ionization nebula. They'll create one that's ionized some gases. And if it's a Wolf Rayet star, it would clear a cavity around this pretty quickly. But I think this is not a Wolf Rayet, but a regular star inside of a nebula. And there may be low amounts of gas in here too. That's my belief. My guess actually is it's not a Wolf Rayet. This is really nice.
It's actually an open cluster inside the nebula there.
Mm-hmm.
So it's more than one star.
Yeah.
The nebula is illuminated by a magnitude 7.4 star designated SAL 19158.
Okay.
Doesn't say what type of star it is.
Okay. Cosmic Ray, I'll get to your question in a second. Which I did answer. You may not have heard it. You asked me, what's the dust composed of to give it this light-absorbing quality? Well, the dust are micron-sized particles, okay? And it's made of, as I mentioned before, silicate compounds, silicate molecules, and carbon molecules, and carbon atoms. And they will aggregate into dust particles that are a couple of microns in size, not very large. And these dust particles are very capable. When you have more of a light year of them across, the dust particles are very capable of actually, absorbing starlight and preventing starlight from getting out. Again, it's the depth of the nebula, the size, the three-dimensional size. Now, one of the confusing things is, I mentioned that you might have 10 atoms per cubic centimeter to 50 atoms per cubic centimeter, but I just talked about particles. So what's the difference? Okay, in a nebula like this, which is full of particles of dust, we're talking about what we call a very Spartan placement of these particles. There's very few particles, all right? And because they're only a few microns in size, we're talking about a density that's very, very low, all right? And very low density areas we're going to find out in the universe like this. So the dust particles are not highly dense, okay? They're not nearly as dense as the molecules in our air, okay? And if we think of dust in the air is much more highly dense in a local region, local amounts, than in this nebula. Now, he says, how do we know this? You can't we spectrum analyze this? Yeah, of course. And we can see, okay, we know, for instance, this reflection nebula is our clue. All right, we can take a spectrum of a nebula, we can see what's inside, and we can actually deduce all the components of these nebulae. All right, and it's not just carbon, it's not just silicon. We've got methanol in here, we've got H2O, water, in the molecular realm as well. We have hydrogen gas, we have oxygen atoms, singular oxygen atoms. We have formaldehyde ices, we have methane ices, we have carbon dioxide ice, in fact, in some of these places. And in fact, all these dust particles in here, even though there are a few microns around in size or irregular in shape, and in all those nooks and crannies, they actually acquire this material and it freezes there and forms ices deep in the interstellar medium, like out here. This is that's why I mentioned before, these are the cold, dark places from whence life can spring, and from which stars can form if there's enough hydrogen gas. There was enough to make these stars in here that make this small cluster, and they're in the process of clearing out that central part of this area. You can see that this area in here is rather low density for gas and other particles, and these areas out here have a higher concentration. This happens to be an area that was cleared out originally, possibly by the formation of the cluster. Who knows? But this is the idea. We spectral analyze these. We know what these are made of, and that's how we discover that they're made of more than just the silicate atoms and carbon atoms. Now, we also know that when you look at objects like this, right, if we can see them, we can analyze them, all right? Now, the other thing is, this is visual light. There's a whole nother realm when we start looking at the radio frequencies. Okay, if we look at a radio telescope, they can map where these nebulae are in the entire galaxy. They can map out the locations. Infrared telescopes can map the heat that are being emitted by these dark regions, or the lack of heat being emitted by these dark regions. So we have multiple ways to see, not just in the visible light. We're looking in visible light. In the visible light, we see this. But in the infrared, this looks very different, right? In fact, the areas that look dark on visible light shine brightly in the infrared, or sometimes in the ultraviolet, and sometimes in the radio spectrum. All right. So the infrared effectively is the near spectrum. You go out further, you go to the radio spectrum, which is much further out. So there's a lot of frequencies that we can use to attack a nebula like this and decipher what's going on in there. All right.
And
we also have masers and other strange oddities that occur out there as well. So there's a lot going on. I'm sorry. Go ahead, Daryl.
pretty safe to say that the dark cloud here is going to have pretty much the same stuff in it as a dark cloud anywhere else.
Oh, yeah. Yeah.
And you see dark nebulosity, around the lagoon, for instance, and
yes.
It's going to be pretty much similar to what we see here.
It
or
will.
anywhere else in the sky.
It will. And when you ask why that's true, this is beautiful now. Now you can see a real good separation between this and the backdrop. Okay? So now you see what I was talking about. There's stuff here. There's stuff here. It's just filled all throughout here with stuff. The only place there's not much is right down here and in the little voids that we've identified here. Isn't that cool? Interesting, too. We have a void right here, Daryl. See that? The one we always talk about. But then there's another one shaped almost like it. Right down below.
I guess we were talking earlier about star clusters and dust clouds, and the relative age of the cluster is whether it's cleared out the dust around it or not. And
yep.
I would say this is relatively young.
Yeah. And I'm going to do as Cosmic Ray asks. I'm going to save an image of it just like this. So I'm going to save the stack here. We're still stacking. All right, so that's been saved. And then we're going to save it exactly as seen. All right. Now, there's been no noise reduction. I haven't reduced the noise in this at all yet. But you have it now in that promised format. Let's see if we can color correct to bring out one more element. There we go. See the color correction here now. I wanted to try and differentiate and show you the difference between the black of space and this dust. Now you can see the dust. If you can see the dust as brown, you can analyze it in visual light as well. Okay? And Cosmic Ray says the smoke nature of this region is amazing. Yes, it is, Ray. Yes, it is. And the dust is made of everything I just mentioned too. The silicate molecules, the carbon molecules, and silicon atoms, and carbon atoms, as well as the ices that adhere to these particles. It literally makes a slurry from which planets and stars can be made. Again, as long as we have enough hydrogen gas to make the stars. You don't make hydrogen gas from dust. I'm sorry, you don't make stars from dust. You make stars from hydrogen, primarily. Okay? So, this star cluster forming here had to form from plentiful amount of hydrogen in order to actually be here like this. So it might have blown it all away, because hydrogen is much lighter than the dust, so the dust will stick around longer.
Right. So all we see is the blue reflection nebulosity.
And that process plays out all across the nebulae, like the Trifid Nebula, and others.
This is Cepheus again, isn't it?
I think that this is. We're here now. This is Cepheus. Yes, it is.
Yeah.
Yeah. Let's center
it's
up
interesting to look at various areas of space, constellations, if you like.
Yeah.
I mean, I know once upon a time I didn't think there was much interesting to look at Cepheus, and
Turns out
this
there's
is
more than believe, huh?
yeah. Well, if you follow the Milky Way up from Sagittarius in the summertime, you're going to go up through Cygnus, and then you're going to go into Cepheus and on to Cassiopeia, and down through Perseus and Taurus, and into Orion in the winter Milky Way. But you know, there is a lot going on in this constellation.
I agree with that.
We tend to see all sorts of nebulosity like this.
Michael Hedrick says, beautiful. It is, isn't it? It is really stunning. Let's see if we can pull out even more detail here. I think we've almost maxed out what we could do just from a processing point of view, but we can do a little more here. Notice the subtle lighter tones down here. Let me just gesture that away. And now look down here. Okay, all right down here. Check this out, right there, coming down along this line. This is a beautiful line, and these are these denser areas here. These are areas that are gravitationally condensing. Okay, in all likelihood, so there's going to be something possibly happening there in the future. Maybe more stars will form out of that if there's hydrogen there. If there's not, well, guess what else can happen? This is something kind of new that we didn't know as astronomers. That planets could form by themselves as rogue planets with no star. And that's also a possibility. Some of the research shows that you might have a significant number of rogue planets in our universe, which is kind of cool. You know? Kind of reminds me of Space 1999, that show was in the 80s, or 70s, that basically the moon was blasted away from the Earth because of a bunch of nuclear explosions on the moon. Even back then I knew it was a silly premise, because certainly that wouldn't have done it. But okay, it wasn't good science fiction, but it was all we had. So it was actually kind of fun to watch it. All right. And so in that, the premise was the moon became a rogue moon, flying through the solar system, flying through interstellar space. And how it could actually end up leaving the solar system in such a short time and meet up with aliens, I don't get it. Okay, but again, they needed a show. And the show needed to have new aliens every week. And they were just really badly made.
What show is this?
Space 1999.
Oh.
With Martin Landau and Barbara Bain.
Yep.
Yeah. They'd go to open the doors and go, and the doors would open. That's what they would do. That was the sound effect, go and go at the same time, and that was actually the sound. So they point this thing. They had to point the thing at the door to go make the door open. They didn't just open like on Star Trek. So for all their advancements, they didn't have automatic doors. It's kind of funny.
Might want to save this again.
Ooh, yeah, look at this. Yeah, this is a beautiful view. Yep. We're going to save it again. We're going to save it right now and save it exactly as seen. This may be one of the best ones. I know I keep saying that, but as we improve and get better things, better technology in place, our imagery comes off just beautifully. I mean, I'm really, really happy with this. Cosmic Ray says, Mark, we must get you to the dark side. Well, maybe so, Ray. You may luck out with that. But in fact, I already have part of it. I've got my Vader bottle here. I think some of you remember the Vader bottle. Okay. Let me just show you the background. By the way, that's the telescope right there. That's going to have the spectroscope system on it. That's for our new building out here. This is the Vader bottle. I made this bottle a full. It was backwards because I got the camera backwards. I made this bottle, or made this thing, a full 25 years ago, and it still works. Listen, I'm Mark, and now I'm Vader watching.
You are part of a rebel alliance and a traitor. Take her away.
Oh, yeah, it did. See? I haven't broken this bottle. It's perfect.
I am Lord Vader. What is it, my master?
Ooh. So, I guess, Ray, I'm at the dark side already. I've been at the dark side for a long time. But probably not the dark side you're thinking about.
Cyclone has a question of you.
Cyclone. And what is Cyclone? What does Cyclone add? Okay. KIC. That's Kepler Index Catalog 9832227 binary star system. I'd have to look that up, Cyclone. Okay, otherwise known as MPC. I'd have to look that up. I'll have to look that up. I don't know offhand. I know some things. I don't know all things. You know, Daryl knows all things. I'm just an astronomer. He's an astronomer's astronomer, right? He's the guy that builds telescopes. You know, you're more familiar with the actual night sky than I think than the way objects may work in the night sky. And sometimes people want to hear that more than they want to hear like what they are. So I think that's a good combination between us there. Okay, let's see here. I'm color correct.
I have a clue about
What's that?
KIC 9832227.
Yeah, no, I'd have to look it up.
So would I. I mean, somebody's pulling rabbits out of their hat.
What do you mean?
Just seems a very random question to ask.
Well, there are some people that actually think about some crazy things out there, and the universe has got a lot of crazy going on, let me tell you.
Let me look it up.
Well, I mean, I know it's a contact binary. Is that what you're talking about? Contact binaries are really strange. It's off somewhere like Cygnus or Aquila. I think it's in Cygnus. What a contact binary is there's two stars that are orbiting each other that are so close to actually their atmospheres are kind of in contact with each other as they rotate around. Izabela says it's a contact binary. Okay, so it is in Cygnus. Okay. Yeah. And okay, yeah, so that's contact binaries. Boy, oh boy. I would not want to be anywhere near a contact binary system because nothing but trouble can follow. You know why? Because eventually one of those stars is going to die, probably before the other. And that means it's going to swell into a red giant. But as a contact binary, that means that the second star is going to be entirely inside that first star, most likely. And that's probably going to spell disaster for that first star. Could cause it to go supernova, I don't know, depending on the mass. And so that could be pretty darn exciting.
It's an eclipsing binary too, and
11-hour period.
we must be on the same page.
Well, I was just looking at
Predicted to merge in 2022. That's probably why you brought it up.
Okay. Yeah. So if they merge before one of them dies, then this could be an interesting observation to make. Because you got two stars pumping out radiative energy, and then you're trying to combine them into another star. Do you think they're just going to combine to make one bigger core? I don't know. That stuff, when you get close to the core, that's extremely powerful pressure pushing against each core. It'd be interesting to see what they do when they merge. This is great. We're done with this one. We've got literally 47 stacked images. That's more than we've ever done. And so we're going to pause this now, save it one last time, and save it exactly as seen. This is going to make sure we have very little noise in the final product.
Very nice image.
It is a gorgeous image. So I want to thank you guys for your patience and letting me just run through that, because I thought this would be a really good thing to do. Especially tonight, because the sky is stable. We don't have a lot of that wind that we had the other night. It makes it really pretty. All right, so, and that was a 40-second exposure, so we got lots of detail. All right, back to our 1-second exposure. Kind of spoils you, doesn't it, to see this? Knowing what we had just seen. All right, so let's check out now some of the other objects around us now. We've seen so many. Well, let's go over here. We got, let's see, it's 11:30 here. We started with the double cluster. We're just going to continue to go this way. I don't think we can get to the flaming star yet. Yeah, I want to show you this. Show you guys this. It's not quite there. We need to have it up around here. 45 degrees up from the horizon, because it's off the back of the telescope, that way, in the image. So the telescope has to be pointing way over here, and it's going to be pointing into the building here. All right. Let's go over here. Daryl, feel free to offer up objects if you like. I've got one we're going to do while you're thinking of that.
It's too early for that one I had in mind.
Okay. We're going to go to Navi, and we're going to do the Gamma Cas Nebula. Because now that we can support longer exposures, I've never done more than a 25-second shot here.
Shared that image earlier today of, well, there were three. The Wolf Cave was too dim. I think the one was Sharpless 2-126.
Yes, we can do that one.
And the Lion Nebula, those would be interesting.
Okay.
Izabela asked about the Lion as well.
Okay, we will do that. We'll do that. We'll take care of this one. Look at that. Gamma Cas Nebula was dead center. Not bad. Okay. So let's check out. Let's move just a little bit to the west, tiny bit. Okay, star lock is gonna lock onto a star, start doing their thing. We'll prepare the exposure for 40 seconds and get ready to go. You watch up there, you'll see the searching changes to a zeroed out starting calibration. There it goes, and then off it goes. Now we let it stabilize, and it's guiding for about 5 seconds. It takes about 13 seconds to get a guide star, and I let it stay another 10 seconds or so before I start, and that prevents initial issues with guiding. Okay, so now we're going to come down and do our stack, and we'll see our iris here one last time. That's what it looks like natively, and if you check it out, look how beautiful that is. That's the kind of detail we get after 40 plus exposures. Look at that. Isn't that gorgeous? You see tremendous depth in there. So we'll have that in a better format for you to see. So we're going to clear that. It's out there on the drive already, on the database, I'm sure. And this is the Gamma Cas Nebula after 40 seconds. There we go. Look at that. Gamma Cas, otherwise known as Navi, N-A-V-I. That's actually a really bright star responsible for ionizing this hydrogen gas in here, and the dust associated with it will scatter the light from Navi too, so we actually see it as an emission nebula here and a reflection nebula there, and emission all throughout. And we'll get that looking a little better here, so you can see a little more of what's going on.
I'll be darned.
What?
I looked up this sharpless object.
Yeah?
It's in Lacerda. That's another one. I never thought there was anything interesting in.
I know, right? That's Sharpless 2126, right?
Yep.
Yeah, I discovered that last night. Is that the Lion Nebula? Or is that the, No, sorry.
That's the Great Lacerda Nebula
That's
or
right.
the Star Funnel.
Yeah. Yep. Okay.
Yeah.
Izabela, thank you so much for putting those links out there. That's very kind.
We can look at that after Gamma Cas.
Yeah.
Cosmic Ray,
See it out
Izabela has a question of you. I think she's had a problem seeing your comments for a while or something of the sort.
Okay.
Cosmic Ray, can you see Izabela's comments?
There shouldn't be any reason why he wouldn't. He says he does not.
Somebody may have blocked him, or
Blocked
he may
her.
have blocked her.
Well, Cosmic Ray has a wrench. He could have blocked her by accident. But he would block her from the stream. Right?
I think if somebody blocks somebody, that other person is blocked from seeing their comments also.
Yeah, I guess that's possible. So, Izabela, check that you didn't block Cosmic Ray by accident. Because I know you did that by accident with other folks.
Both of you hover your mouse over on the right side where the three dots show up, and then click on them. Good night, Hedrick.
Oh, is he going to bed? Where they just at? Oh, okay. I will say good night for now, but thanks for a wonderful time. Michael Hedrick, thank you. It was nice to see you here again. Good to see you, brother. And you have a good night. Remember, keep looking up, brother. All right, we stacked 7. We're only going to go to 10 on this one. Because I'm really excited about going to that other one. Okay.
So you don't see Izabela.
Yeah, he does not.
Sounds like somebody blocked somebody accidentally. Izabela says she sees his comments during the stream, but they disappear for her after the stream. Maybe it's a glitch.
Cosmic Ray, be honest. Are you a time traveler? I think Cosmic Ray's a time traveler and he's not sharing that with us. You sneaky little guy, Ray. Let's pull this out. Let's get some more detail out of this. Let's see what's hiding in here. Here we go. Look at that. Now you see the extent of this nebula. And we got a color correct it for the blue here. Here we go. Check that out. Here's the Gamma Cas Nebula. This is the most prominent feature of the Gamma Cas Nebula right here that people see all the time. Okay, and talk about is this feature right here. This is a beautiful feature it looks like it's being eroded, but this is dark nebula in here as well, and so we've got some stuff in here that's really complex. And we also have this reflection nebula we talked about here, but look at the fringes. There's ionized hydrogen in here giving way to dust, all right, which is then scattering blue light. So this ionized hydrogen doesn't just stop here, it just tapers off. And what's actually increasing in density is the dust. So as the hydrogen gas tapers off, the dust tapers in. And so it goes from a dominance of hydrogen alpha emission to a dominance of scattered starlight to create this reflection nebula.
I assume Navi is the source of the excitation.
I believe it is. It's very complicated, though. If you notice over here, okay, we have a reflection nebula with another ionized region, with another region, another reflection nebula. It's just mixed throughout. So there's lots of dark dust in here. All this is dark dust. And these are areas that just happen to be visible from our location. See, this is all dust that's peeking over. And this is probably behind this, and this are part of this entire region. And they're probably, if you move this out of the way, you're probably all connected. We just can't see it, which is kind of cool. So that's neat. And there's more over here. Okay, so we got 12. We'll go to 13. Lucky 13. My first house was number 13. It was very lucky for me. All right, so we'll pause this now. We will add in what the name is here. Gamma Cas Nebula. And then we will save it and do our save process. It'll be up on the database in a short period of time. Save exactly as seen. And then clear it. And now I want to go to Sharpless 2-126. Sharpless 2 is a catalog. And so that catalog is something that we can search in. Look at that. There it is.
I read somewhere once that some cosmic rays are so energetic they have as much energy as a thrown softball.
Wow. Well, our cosmic ray is pretty energetic, isn't he? I mean, listen to him. He's got a lot of energy, right? Oh, you mean the actual cosmic rays.
Can you imagine being hit by a particle with the energy of a softball?
Oh, gosh, no.
Sometimes when you see flashes of light in your eyes, those are cosmic rays hitting your eye.
Well, interesting you mentioned that, because I did, one of the shows I did, I think it was What on Earth. One of the episodes, I had to go through what was causing the Apollo astronauts to have these bursts of light in their eyes. And we had to, well, that's a pretty mosaic. We had to talk about that whole thing, which was cosmic rays hitting the retina and causing those flashes. Those flashes are also known as phosphenes. So we see that too, you know. But I'll tell you, it's pretty interesting how that works and how the human brain and eyes react out in the middle of space.
Aren't phosphenes what you see when you press on your eyes?
Yes. Yeah. And they look identical to what the astronauts see, kind of. If you press in your eyes and you see these things in your eye, you see lots of them. But the astronauts would see flashes. Flashes. And those are the cosmic rays striking their retina.
Yeah.
So, if you think about it, it means we can see cosmic rays. But Izabela can't see cosmic ray. It's getting complicated. Okay.
I remember I was listening to Led Zepp 2 one night many years ago.
Yeah.
On a quadraphonic stereo, and I was sitting there in the dark with my eyes closed, and I pressed on my eyeballs, and boy, I saw phosphenes out the wazoo, and then I saw a little guy come running right out of one of them.
I think that was probably the substance you might have been imbibing in association with the Led Zeppelin album.
Me?
I'm such a geek and nerd. I've never tried any of that stuff, you know. I just never have. Okay. We're guiding stably, and I'm going to now kick in and go to our Sharpless 2-126 object, which I think should be pretty interesting. And I'll change the name up here now. SH2-126. I'm just taking this first picture. I probably should have got its placement. Cosmic Ray, you don't have to turn on nerd. We know you're a nerd. You're one of us, man. I think everybody that's here, in a sense, is in love with intelligence and stuff like that. I think it's great. So this is the beginnings of it right here. Right here. It goes all the way down like this. And it's actually a prong that'll come down here that you'll see in a little while. As I said, I did research last night with this object to see where it falls in. Mathematically formulate an elephant trap, please, says Sean Farva. Well, I can do that. In fact, in Indonesia, they've unwittingly found these. The elephants tend to fall in holes, and they can't get out. They can't just like hop onto, like a dogs hop onto a bed. They can't hop out of the hole. Once they fall in the hole, if it falls in higher than the top of their legs, they can't get out.
Yep. There are lots of videos on YouTube of elephants falling into holes.
And they use tractors and backhoes to get them out.
Yep.
Uh-oh, but Izabela can't see my words, Cosmic Ray says. My heart is broke. Izabela says, sometimes I see flashing dots when looking at the sky, but maybe it's something in the eyes. Okay, yes, it could be, but you might also be seeing a tumbling satellite, too. And the thing is, one of the problems we have with our eyes, something I talk about, actually, I teach, is something about, it's called the autokinetic effect. You know, when you look in the sky at night, you're staring at an object, you're seeing something flash in the night sky. You keep staring where you think you're looking at that same spot, and then it flashes somewhere else. So you look there, and think that's where it is now, and then it flashes over here. But wait, now it's over there. And you see it flashing, and it looks like it's flashing in all these different locations in the sky, over here, over here, over there, over there. But in fact, it could very well be just moving in a straight line across the sky and brightening and dimming, brightening and dimming. But your eye, and this is the Stanford University and the Eye Institute did this study to show that you can't judge dark night sky. You can't actually keep looking at the same spot. Your eyes are always trying to search. It's built in. You can't stop it. And that's called the autokinetic effect. And so the autokinetic effect has been responsible for a lot of UFO sightings, a lot of people saying it danced all over the sky, it moved all over the sky, when in fact it may not have moved over the sky, but moved in a straight line slowly across the sky, but flashed. And I had 40 people around me doing a sky watch out in Arizona. And we looked up in the sky, and they said, "Oh, look, there's a flasher. There's something flashing." And they would shine lasers at it and then say, "Look, it's responding," when they finally saw a light flash, ignoring all the times it didn't flash. So, right? So I quietly was taking a picture with my DSLR system, a Sony a7S II camera. I had it on wide field, and I was taking a photograph of that area of the sky the entire time. And when they said, "We saw a flasher and it responded to our lasers," I said, Are you sure that what you saw was, moving around the sky?" "Absolutely, without a doubt." "Oh, okay. And where did you see it move?" "Well, it was here and there. It started going all over. It had to go like 20 degrees circle. It was going all over the place. So it was moving all around that circle." "Yeah." Other people said, "No, it was a much finer circle." Other people said it was even bigger. And I said, "Okay, what if I told you that I was taking a picture of that area the whole time? You want to see the photo?" "Yeah." So I showed them, and we saw a bunch of dashed lines going across the sky. Why dashed lines, folks? The dashes were where the satellite was blinking as it was tumbling. It got bright. Like if I do this, you don't see much. When I do that, you see a lot more. So as it tumbled, you saw that aspect ratio change, and you saw it get bright and dim, but it was going in a straight line, and they didn't realize it. In fact, most of them swore that couldn't have been the right photo, and I was like, it's looking at the sky you were just looking at. The exposure is literally seconds old. And they were blown away by how much their eyes can fool them. Look at that. We're starting this now. This is looking good.
I don't see much.
Spoil sport. Why don't you just wait it out? I'll show you. So there it is right there. We got filaments there, filaments there. We've only got 8 stacked, so we've got to go a little more. In fact, I might be able to color correct some more detail in. How'd that work? Looks like an open snake's mouth right here. There's the eye, top jaw, bottom jaw. This is what I think is really interesting. There's an interesting thing right here that we'll see develop here soon.
Some of this is actually going out the field of view to the
Oh,
left.
it certainly is. Let's try and find some more data. How's this? See that? This whole thing right there? You do see that, right?
I'm sorry?
Oh, okay. I was telling you do see that, right? You can see you can see this thing right here.
Yes, I see that.
Oh, okay.
I
Just making sure, because sometimes people have their monitors set to not be able to see those kind of contrasts very well. I didn't know where your monitor is set. We actually never calibrated your monitor, Daryl.
well,
Yeah, well,
I'm trying to compare what's on your monitor with the image I'm looking at, which
what about the image of this I sent you earlier? I sent it to you.
Yes, I'd have to open it. I know the image you sent earlier showed a lot more detail than this, but I assume it had post-processing in it.
It did. But by that I separated the stars out from the nebula, and I worked only in the nebula. Cosmic Ray, do you see Izabela now? She's asking you.
Yes, I'm looking at the image you sent earlier.
Okay. And now Cyclone has his other ID running up and going, okay. Oh, you have an AIT account. Wow. I used to have AIT for my internet years ago. Cosmic Ray does not see you, Izabela. Okay. Hey there, Papa Tom. Nice to see you, man. I'm glad you showed up. We're doing fine, man. Looking at a bunch of things. Taking some cool pictures. Let's see if we can drag some more detail out of this. Oh, look at that. These are extensive light years long clouds of silicon materials and carbon materials along with ices of all kinds. This is just so cool. Look at that. Wow. It's almost like the stars almost get in the way sometimes. Which Daryl won't say because he loves the stars. He's told me so.
Say what?
You've told me that you actually like seeing the stars, but they get in the way sometimes of actually seeing the nebula.
I like stars.
Yeah.
I'm flipping back and forth between another image of this and your image, and you need to do a mosaic of this.
Oh yeah, it's huge. I know. You're right.
Because you're capturing only a very small part of it.
I am. I wanted to capture this section right here. This looks like a fish. You know, a fish fighting in like the eye, the mouth, the LED in the nostril. You know, I don't know.
You're down at the bottom right-hand corner of the larger nebula.
Yeah, I am. It's up there, out of the view. At some point, we will do a mosaic of this. I agree. Yeah. I won't do it tonight, though, because I don't know that I don't want people to have to sit through that. I'll actually do it in a private session. Yeah, good. The guiding is perfect, though. Look at that. Stars are round, which they should be. We got a little noise. Let me see if I can... Let me add a bilateral filter to this, which could possibly knock out some of the noise. All right, let's see. Okay, now let's back out and see what it looks like.
Okay. Actually, I was looking at the... you're zoomed in some. I was looking at your image that you sent earlier today. Yeah, this is just a tiny part of the whole nebula.
I know. You're right. It's huge. But we got to start somewhere. And I wanted to do this section because this is, I thought, a very interesting section in the nebula. And interestingly, this is a different lighter. It's a lighter seemingly color. And this is darker. I think this is a soft glowing hydrogen emission back here, but I have to look and see.
I just sent you the other picture I've been referring to.
Okay. Yeah. I certainly don't have a wide field like that. But it looks pretty, though. That's a beautiful image. Yep. This is such a huge object that this is probably 8 or 10 image frames here. Let me actually let me go to auto so we can at least get the just get it exactly right. So there's the full size of the image. Okay, frame. And we'd have to add probably a full 7 more just to get the bulk of this nebula.
Mm.
Maybe even more. But it's stunning. Look at it now, isn't it? See how it's starting to come in? We're
Yes.
starting to see so much more detail. And that's why we stack, guys, to just really start to show the detail that really exists there. Really something. Let's see if we can go in here. Let's take off the bilateral filter, see if we can get rid of it now. May not need it. Okay. Because the bilateral filter is destructive a little bit to data. And let's see what this wants to do. Yeah, I like pulling back our data. We'll go back to this other histogram here in a second. Now let's go over here and pull some data. It actually goes the opposite way because it doesn't. All right. There we go. Let's come out of this now. Look at that. That's cool. Now let's darken it up and actually pull this into the peak of the dark a little bit.
Can you punch up the red?
Yes, I can, as a matter of fact. I was sort of doing that passively. I didn't want to add the red over here, but I will. That's too much. That's better. That's pretty cool.
Mm-hmm. Looks like a little worm or fish shape there.
Yeah, that's the one I was telling you was the fish, I think, was this guy. With
That's
his
got a face
flapping
on the
tail.
left.
Yep.
Kind of like a crooked smiley face.
Yeah.
Excuse me a moment, please.
Okay.
Back.
Right. All right, we have 23 stacked. I'm going to go to 24 on this, and then we will halt it. Let me get rid of this artificial processing here, just to show you a little bit about how much noise we get rid of once we do this many stacked images. And you see that? Okay, this is pretty. If we get rid of this guy too, you can see there's no noise in here, and just the slightest indication of nebula. Right? But what's really hiding in there is all this. See that? That's what hides in the dark. I love it. And then we'll just add more data by pulling it in like this. And we'll do that offline too. But we'll save the picture just like this. Thank you, Papa Tom. Very nice of you. Okay, so there's 25 stacked, and we're gonna pause it from here, and we have Sharpless 2-126 up there. We're gonna save it. Save exactly as seen. All right. Then we're gonna punch it up a little more. Punch it up a little more here. And look at what we've got. All right. And that's pretty bright, but that kind of shows the overall extent of what we've got there. And now I'll save the image exactly as seen again, because the raw file is unaffected by everything we're doing. If you save exactly as seen, then it saves what you see here. So that's really cool. All right. Let's now clear this and be ready to move along. Move along. Nothing to see here. Everything to see here. All right. Here we go. Now from our night vision mode, we can see that there's hardly anything visible there at all. Daisy and Zoe Amethyst say it looked like a worm with two bright eyes. Yeah, well, these are the bright eyes, right? Kind of funny. Thanks for sticking around, Daisy and Zoe. Okay, let's now... let's head over here. Okay. Okay, we're gonna take a photo of the elephant's trunk tonight, but we're gonna use some differences in the way we take the picture because we can. We're gonna actually photograph it with a slightly longer exposure and do some of the same things we're doing with these other exposures to kind of pull some of the detail out that we have yet to have done. Okay, you can see the nebula here. At least it's all throughout here, actually. And the elephant's trunk itself, I think, is right here. I'm going to zoom in just to see. Okay.
What are we looking at now?
Oh, I just brought us over to the elephant's trunk.
Oh.
All right. What I'll do is I want to see exactly where we're looking. I'm just going to do a quick 20-second shot of this region without stacking it, just to get placement. I mean, I see what's going on here. I just want to get the proper placement. Yeah, it's okay. That's what I thought. So there is the elephant's trunk in that dark nebula. That's just what I thought we were. So it's pretty good. Pretty good. All right, these are the stars that we're interested in right there. So what we're going to do is we're going to move up a little bit. And then move a little west. That should be good. A little more. I'm gonna pull in the stuff from the right here that we don't normally see. All right. So we're gonna pull this in from here. We're calibrated. We're guiding now, and we're gonna do a 40-second shot here and pull out details. We're doing this at 400, by the way, which is a higher gain than we normally do. All right, now we'll live stack it. All right, and we're gonna clear this and say go. There we go. Okay, stack is clear and is renewed. All right. Alrighty, and let's take a look at the Elephant's Trunk Nebula. This is an emission nebula with dark nebula everywhere. A veritable playground for new stars. Look at that. Wow. Let's adjust it a little bit.
I see the caravan.
Yeah, and there's a, looks like a tumbling satellite right here. This is the caravan, the camel caravan. NPC, otherwise known as Cyclone, is hungry. I think that's pretty obvious. Okay, let's yeah, see that tumbling satellite going through up slowly up there, guys?
Yeah.
I just talked about that. That's what I was taking pictures of. There's a lot of tumblers up there, as I call them. All right.
Typically tumbling rocket bodies, aren't they?
Yeah, they're like spent stages.
Yeah.
When they disconnect, there's some momentum that's imparted to them slightly, whether they're rolling or tumbling a little bit, because they don't disconnect perfectly from the main rocket body. Some parts of it do get a little bit, for the most part, they're released perfectly, but there is enough of a variance that imparts some kind of motion to it. On top of that, the solar wind striking one side of the rocket body will cause it to tumble and do things like that. Even the James Webb Space Telescope has to counter that. There's a flap on the back of the James Webb Telescope that just sits up, and people say, well, what is that? That's actually effectively not a rudder, but it's a corrector that corrects for the stellar winds from our sun hitting the James Webb and moving it unexpectedly. So it actually, where the stellar winds are trying to push it this way, that flap is up to keep it, keep them hitting that flap by just enough to keep it negated, to make sure there's no wind at all hitting it. No stellar wind, no solar wind. Pretty cool, huh? All right, let's look at this.
It has a name. I forget what they call it.
Yeah, I can't remember right now. So this is beautiful. Also coming into play, you're going to see a beautiful reflection nebula right here that you'll see forming slowly as we get more exposures underway. But look at this beautiful rich region of nebula. This is what they call the elephant's trunk. This segment right here. Look at how spindly this dark nebula is. But also note the color. Okay. It's dark nebula mixed with hydrogen gas, which itself is ionized. And that does cause this object to look really strange sometimes. Do some more contrast enhancement for you. Let's see what this shows. Okay, this will just be to kind of give you an indication. We won't keep this because that's really a little too bright. But overall, okay, you can see the extent of the nebula. And then we have this very, very dark area here. That's a several light years thick cloud of particles.
Shame on you, C&D boy.
I don't understand. Because he timed out NPC?
Yeah.
Oh, I'm not sure. One of the messages that was hidden was, "I'm sorry, my little brother had too much sugar and he's going crazy on the phone." Are you saying your little brother is the one that was typing the messages that got you timed out? Oh boy. Yeah, C&D boy did it by mistake, so don't worry about it. You'll be back in no time. And there's no permanent, there's no detention and no permanent demerits. Okay, you're still good. Look at this. This is beautiful.
Again, Cepheus.
Yeah, this is this guy right here, and we are in. It's circumpolar, obviously, and constellation is Cepheus, indeed. It's over this way. See, it's at the base of the house.
Right.
Cepheus looks like a house, guys. See this 1, 2, 3, 4, then the peak up here. And you can see that from the ground, from here looking up. And then right below the base of the house, in the foundation, is this. The beautiful Elephant's Trunk Complex. Molecular clouds and emission nebula. Really something else.
I said earlier that Cepheus has a lot going on, and it. I wondered how you might typify. Has it got a name? What the heck is happening in there to make it so rich?
That's a good question.
It's just along a spiral arm, I guess.
Yeah.
Being so rich for being so far from, where you generally think things are happening in the Milky Way, which is down towards Sagittarius and all that.
Yeah.
There's a whole lot going on here as well. Last I heard, James, yes. That's a big subject. It's interesting if you can find a display of what it's doing at the moment. When the third stage, the translunar insertion happened last night, I wound up staying up till, almost 2:30 in the morning watching that, and then I read a little while. The craft was moving 22,500 miles an hour, and I saw it this afternoon, and it was moving down to 7,000 miles an hour or so. And it's slowing down so much because Earth's gravity is pulling on it.
As it's leaving.
If you're old enough, I'm sorry.
Yeah, as it's leaving the Earth's gravity well, it's being tugged on by the Earth.
And if you're old enough to remember the Apollo missions, this Apollo spacecraft did the very same thing. They left Earth at about 20, maybe a little less than 25,000 miles an hour, and they slowed down and slowed down and slowed down until they got to that equipoise moment between the Earth and the Moon, where the Moon's gravity was greater, and then it started speeding up again. But it's coasting and it's slowing down all the way until it gets close to the Moon. And it's taking such a leisurely orbit, I dare say it's going to slow down a whole lot before it starts speeding up.
Yeah, I'm pretty impressed with the Artemis program. I think it's interesting. I don't like the boosters, as we said earlier, but they couple Artemis with Elon Musk's Starship, and we have a winning program there.
You really think that's going to happen?
I can tell you this, okay? One of the Starships finally landed, and it, obviously it landed fine, and I think that, again, how many failures were there along the way in the Apollo program? We lost people.
Yep.
Grissom, Chaffee, and White on Apollo 1. So that's, you learn. Don't breathe pure oxygen. Don't pump pure oxygen into a capsule. Slightest spark will set off everything on fire. Look at this beautiful location. This is so stunning. Really
Ad astra per aspera. I don't speak Latin very well. That means to the stars by hard ways.
Oh, yeah. Okay.
I think we're going to see the Chinese flying SpaceX style before we see NASA fly SpaceX style.
Well,
Chinese are already working on reusable spacecraft.
Yeah.
Reusable rockets. And I bet you some industrial spy probably stole the plans from SpaceX.
Well, I don't know that I don't know that it's something in the plans that could be stolen. I think it's a culture in there too, of people striving for success. Every SpaceX launch and booster landing, you hear cheers, and that's not fake stuff. These people are really excited. They're young, they're ambitious, and they want to see the program succeed. So the program succeeds. In a country like China, are there people that are that ambitious across the entire gamut? They pretend to be ambitious, but they have a domineering, big brother always watching them. So how into their systems can they actually be? How devoted? Nothing comes out of it for them personally. They just have the privilege of working on a space program, but the Chinese Communist Party takes all the credit. So,
well, Chinese nationalism is the thing, though. A lot of people are proud of what China has achieved, and I mean, they're going to be eating our lunch one of these days if we don't keep up with them.
Well, manufacturing-wise, we've already, we owe them trillions of dollars. So the truth is, they're not going to eat our lunch; they're going to make our lunch and sell it to us. Okay, they're an economic powerhouse, and that's the thing. If they ever stepped into a conflict between us and another country, we would simply not pay their bills. So I'm not paying you any money, and that'd be the end of their money, and that would really seriously injure the Chinese economy and their ambitions. So they're on a very delicate tightrope. They better remain neutral in things, or else they're going to end up losing everything. Because if we decide not to pay our bills, that's billions of dollars they don't get.
I remember when the Chinese couldn't even get a rocket off the launch pad.
I remember that too.
And money crossed hands, I'll just leave it at that, and they suddenly had the technology to do it.
You don't have to leave it at that. You can say what it was.
It's political. I'm liable to piss off somebody. Pardon my French.
Well, the truth is that politics came into play, and
all right. Well, somebody was looking for campaign donations, and the Chinese gladly gave them campaign donations in trade for American rocket technology.
Yeah.
And this was back during the 90s.
Mm-hmm.
Before that, they couldn't get a rocket off the launch pad. And see what they're doing nowadays.
Yeah.
Chinese probably have the most ambitious rocket program going on the planet right now.
Yeah.
They're launching a whole lot more often than we are. And they're not afraid of failure. I mean...
No, because they don't have any concern for the people involved. They just care about the outcome.
If it's bad enough, they'll just take them out and shoot them in the back of the head.
Isabella says this is a beautiful rendering of the trunk. I have to agree.
Yeah.
I'm seeing some beautiful elements over here. Here's that thing I told you about right here. This blue little sliver of blue reflection nebula. It's also in this entire area. You can see it. See that? That's beautiful.
I do.
Very nice. So I wasn't trying to take you off task there, Daryl, but I was just actually
that's okay.
trying to bring us back here.
Oh.
This looks really pretty.
Well, we got off talking about rockets.
Yeah, we did. But, you talk about rockets, you can't help but talk about, the countries that utilize them and put them into play. Look at that.
The Russians got their hands on the American space shuttle plans. Look what they did.
Yeah, the Buran, which never actually took off.
The thing was almost a carbon copy of the U.S. shuttle.
Yeah, it certainly was. Look at this.
The old saying, imitation is the sincerest form of flattery, but
yeah.
Anyway, that's where we are nowadays.
I think it's really interesting. At this side of the elephant's trunk, there's this dividing line that's pretty weird looking.
Yeah.
This is not a camera artifact, I don't think. I gotta look and see. I don't think so, because we have, like in the Heart Nebula, you see all the nebula all around through. So this is just a weird shaped nebula. It's always had this shape. Let's take a look at this dark nebula up here. This is an incubator of stars and planets, I'm sure. Look at that. It has a little fringe around it. What about this? What does this do? Yeah, and how about if we throw in a little more? Yeah, look at that. So this is obviously too bright, but it points out and shows you the contrast between this dark nebula, which is truly dark nebula, and the dark nebula mixed with hydrogen gas, which is ionized by the stars in this elephant's trunk region. Well, there's something I haven't seen before, not exactly like this. Look at this. This kind of is there's sort of like a connector here. A faint material that comes all the way through here. See that? Very diffuse hydrogen emission in there. So if we bring this down to what it wants to be, then it would be like this. And let's actually bring this down.
That
Yeah, that's pretty.
the blue area you mentioned.
Right here.
Yes, there's actually a dark line there just above that, and then a
Yep.
brighter redder area above that.
Oh, we'll go into that. Let's check it out. Yeah, there's the line. Okay, there's the dark line you mentioned. And here's the brighter area. And this is the rim. Now, there's ionized hydrogen that is in here. But you'll see it seems like this is rimmed by this ionized hydrogen. Actually, the ionized hydrogen isn't just on the rim. It's actually all throughout there. This is just so dense that you can't really see the ionized hydrogen because the ionized hydrogen is not as, I guess, in this case, not as powerful in terms of its luminosity. But this is what I like about this little area. See this opening? This is a hollow, most likely created by this star, possibly that one. When these stars formed in here, they generated this very powerful stellar winds of their own, which blew out most of the gas in here. There's some dust left behind, as usual. See, dust gets left behind before the gas, but it's open in here. It's a cavity, which we're used to seeing with clusters. Oh, and Cosmic Ray asked a question. Those folks out there looking at us, can they see through the Oort Cloud? Yeah, the Oort Cloud would look probably... let me see if I can find an example here. Okay, if we're looking through an Oort Cloud, it might be as hazy as this hydrogen is, but it's not hydrogen, it's particles, objects. Okay? And it's not like they're so dense that you can't see through them. If they had an infrared telescope, they could detect that the Oort cloud was very cold, but they'd see the warmth inside the solar system. And if they could look at the planets in the solar system, they'd identify oxygen in our atmosphere, and they would know that most likely that's not generated by geologic means, not generated by other mechanisms, chemical mechanisms, but probably being replenished by life because it's staying in the atmosphere. Oxygen wouldn't do that. It would dive in, as it does here on Earth, bond with iron compounds and everything else that it likes to bond with, oxidize. You know, so it's pretty cool. Out there, they would then see that there's life on the planet here, and they could see through the Oort Cloud. They could actually see through the Kuiper Belt too, which isn't a cloud per se as the Oort Cloud is. And they'd be able to identify where in our star system we would see that. We've actually seen extraterrestrial moons around some planets. I say seen, detected the presence of through mechanisms that could be gravitational orbital anomalies or whatever. And we've seen asteroid belts in other exoplanet systems as well. And they show up in the infrared, right? So it's actually interesting how they show up. And again, radio, infrared, and visible and ultraviolet, those allow us to see very, very different things. So they'd see us through the Oort Cloud, yes.
And I don't know, the Oort Cloud always struck me as sort of a misnomer that it's not like a discrete cloud, like a cloud we get in Earth's atmosphere. It's just a large collection of small bodies.
Yeah. It might look like this haze of ionized hydrogen gas here. It might look something like that from a great distance. Especially if they were looking at a object in another wavelength, Cindy Murphy says, wow, so beautiful. Yeah, this is gorgeous, isn't it? We're actually at 125%. We're bigger than our native resolution. If I bring it down, okay, I'll take it to our exact... Okay, this is 100% on our sensor. This is what it wants to be at. But we can zoom in more. Like Cosmic Ray says, they would see 27,000 pieces of junk around the third rock. It's funny you mention that. I wonder with their technology if they'd be able to see that, see that we have stuff in orbit. They might be able to detect radio signals coming from the third rock, indicating some kind of weird intelligence.
And here comes the old, as I've said many times, I always imagine some warlike alien species detecting old I Love Lucy reruns and declaring interstellar war on us.
You treat your women horribly. We treat our females with utmost respect. But you're saying this like, this is like a 60-year-old show. We don't do that anymore. 60 years? Shh, we've been around for 30 millennia. Oh, okay. 30,000 years. I got you. We haven't. Not since Lucy. Wow.
Do you know Lucille Ball could pick up radio channels in her teeth?
Okay. I did not know that.
She admitted that on the Tonight Show one night many years ago.
Whether she was just being funny for a joke or not, though?
No, something about her dental work or fillings or something. I've heard stories like that before that people,
yeah,
actually get radio waves in their teeth.
Well, I can't say that's too terrible. I mean, when you go to the dentist to give you X-rays, I went today and they gave me a bunch of X-rays, and this time it didn't happen, which is weird. But all the other times that I go to get X-rays, as soon as they turn on the X-ray machine, I feel it in my brain. I feel X-rays going into me. My eyes start to vibrate. I can't see straight for the time the X-ray machine's on for that third of a second or whatever. So it's like, and it's over, but I can't see because my eyes start bouncing around. It's really freaky.
You're weird.
Okay. Granted. All right, so this is at the extreme left edge of our extreme left edge of our field.
That's interesting to see the gradation in that dark cloud.
Yeah. You notice that we have a little bit of blue in here, we might be seeing what looks like a reflection nebula inside this dark cloud, which is dense enough because it's far enough away and made of basically a rarefied environment of very, very small particles spread out over a great distance from each other compared to like dust in our atmosphere. But again, this has got to be a light year or more across, maybe more. So
there's a little one to the lower right of that. Looks like a
tadpole. Yeah, that's interesting because when you see these streaks, it means that something might be moving them out like that. Might be moving stuff out like that. And that something could be another star down here somewhere. Or even a star we can't see. Again, it's a three-dimensional universe. Yeah, we don't have all the answers. Now look at that. We're getting a lot of good detail tonight that we just haven't seen before. Wow. Yeah, look at that. So do you guys like the elephant's trunk? Seems to be a pretty cool, you know.
Looks like a very busy place.
Oh yeah. It is.
Again, something about CPS, it just seems to have its own sort of flavor of what's going on.
Yeah. Wow. Michael Klages, there's something that I'm toying with for the next telescope. He says, because Izabela made a comment, and he said that I can't find her comment. Oh, okay. She says, Mark, do you know what STLS needs? It needs a close-up telescope to look at the details. That's where we're going, but I'll show you how we're getting there. We're going to be changing cameras, and the cameras are going to have smaller pixels. So when we zoom in, for instance, okay, on this nebula, to look at this beautiful area right here, the closer we go in, you notice how it gets sort of pixelated now. See the pixels? We're well past the capability at this scale to see detail. However, if we change cameras that have pixels that are smaller, then we can zoom way further in and see much better and much closer the entire time, but still have a wide field scope. So we're looking at that possibility as well. I'm doing all the math now to figure out whether that's going to work, and if it does, we'll go that route. Otherwise, we will get a higher focal length telescope with another camera kind of like the one we have here. So we're weighing both sides. I'm not sure which way to go, and it's like, I want all of it.
Yeah.
But higher focal length would definitely allow us to, for instance, zoom in.
A higher focal length
allow us to see just this.
Still, a fast F ratio.
Yeah.
Would be ideal. But then you're talking a lot of money.
Yeah, then you're talking about larger aperture too.
Well, yes, sure, but yep, like, you know, take the C14. That thing has almost too much focal length.
Yeah.
But if you put a Hyperstar or a Fast Star system on it, you can still run it at f2, and it is going to reduce that focal length, but it's still going to give you more focal length than you have now.
Yeah. It won't run at f2. It's probably going to end up running like f3 or 4, I would think. But
I forget. I know it's a native f11 instead of an f10, like most.
It might be f3, f3.5 or something. It doesn't matter.
Still.
Yeah. Yeah. See, Michael Clegg is saying a 533 sensor with a 2.6 micron pixel. Now, you guys may understand that He's talking about the ZWO is the name of the camera. It's an ASI 533 MC Pro. That's the one I'm looking at. And it actually has square pixels. This one has rectangular pixels. And the 533 square format is something you kind of have to get used to because we have a rectangular format here. But it's a square image here, right? Almost. Not quite. But, you know, we're looking at the possibility of going to that smaller pixel camera. The 533 was one we looked at. We also were looking at the 6200, which was just under that in price, which is way more than we can spend. You know, and so that said, I'm not sure what we'll do yet. I'm debating. Yeah, I'm debating. Okay, user's gone. Michael Kaga says he's going to get the mono version. That means it's not going to be a color camera, which tells me what he's going to do. He's going to be getting the narrowband filters and taking a hydrogen alpha shot, an oxygen 3 shot, and a sulfur 2 shot. Am I right, Michael? And that way you're going to end up with 3 black and white photos that you can combine and make into a full color image. And then do your Hubble palette and have all the separate shots. Izabela says, I don't understand. That will be like a high resolution camera, like not 72 DPI but 300. No, that's okay. It's Photoshop, which will put your photos into a certain resolution. All right, but the camera is well, I'll show you. If you look at our capture image here, 4,144 pixels by 2,822. That's bigger than a 4K sensor. Okay, so we have the ability to catch a very, very large image sensor now with high resolution. Okay, image rather with a high resolution. We bring it to Photoshop, it defaults to 72 DPI, but you can simply change it to 300 DPI. Okay, inside Photoshop, and the image will get that much larger. In fact, it'll become unwieldy like larger. So yes, and so that's very true, and that's very interesting. Michael says yes, SHO and LRGB. SHO, sulfur, hydrogen, oxygen. So narrowband, very narrow band filters that take slots, and we're doing that now effectively because we're using one filter that does it all, and that's because I want you to see color images. I don't want you to have to, you know, wait and see black and white images turned into color images, you know. That Cosmic Gray. ZWO won't sell to you if you're bad mouthing the Chinese. Yeah, or they'll sell me a bad camera. Yeah.
If I had won the Powerball, I was going to get you a 20-inch plane wave.
20-inch plane wave would have been, haha.
But, you know, I don't know what they have with telescopes in that big a format to serve as a reducer corrector or whatever.
Well,
there must be something out there. But those things have pretty high native F ratios, I think. I forget.
You should look at the University of Colorado. They just installed 2 20-inch plane waves.
Is that?
Yep. Plane wave is a makeup telescope. It's a open truss telescope style, and it's just beautiful. I don't know if they have to cool it, if it's got thermoelectric cooling like this camera. I mean, right now we're running at minus 19.8 degrees Celsius. I actually bumped it up to 20 below 0 Celsius. The sensor is running 20 below 0 Celsius. Because we actually have, you know, if you look at the temperature is 8.2 degrees Celsius out there. That's pretty chilly. It's in the 30s out there. Upper 30s. But look at the night sky. Doing it live, man. This is stunning. Okay, this is way too many stacked. When I love it, it's 53 images stacked. We're going to pause it now, and I'll let it keep doing it while I change the name up here. This will be the very most we've ever thought of the elephant's trunk. It promises to be probably one of the most beautiful images we've ever taken. I think I spelled elephant wrong. I couldn't see exactly what I was spelling there. Oh yeah, elephants. This is the elephant's trunk. Okay. Can't really... Okay, if I have to, I'll fix it later. Stunning. By the way, this is... we're here at 55 images. That's a good place to stop. 55 images is excellent because look at the detail that's come out. At the beginning, we didn't see any of this, right? And now we have it. All right, so we're gonna save this just like you see it here. Nice, it's been saved. We're safe. Save exactly as seen. All right, and we've done it. Let's go back and look at the entire thing and check out what we've achieved. Look at that. There is the elephant's trunk region right there. Absolutely stunning. Gorgeous. Plenty of options to look through these areas and start picking them apart. And now that the camera's focused at the four corners without many issues at all, most, if not all, of this image is usable. It's just gorgeous. Wow. Okay. Izabela, your question is unfortunately impossible to answer. Okay. She asks, okay, Michael Klagus picked up on it. She wanted to know how many square light years is a single pixel, and she smiles. Well, if you're looking at, say, the Elephant's Trunk Nebula at a few thousand light years away, a pixel will be a certain number of light years. But if you're looking at the center of the galaxy, then a pixel will be encompassing even more light years. So you basically have to, it depends how far away things are, as Michael Klagus mentioned to you. All right. Well, there we go. Let's pull this away because we don't need this anymore. And we'll clear it and move along. Been a very good night so far. That was a 40-second exposure too. And there it is. You can appreciate how dim it is because a 1 second exposure with a sensitive camera just barely shows this nebulous detail. So that's not bad. Not bad at all. Okay, and we're way over too. Let's go see what's waiting for us on the other side of the pole. See if we got something to look at. Okay, let's go look over here now. Okay. I think we can do this. Let me check. I think we're good. Alright, we're going to go for the Flaming Star Nebula. And you're going to see the telescope swing way over to the other side here. It went right by. Mars is right there.
Whoa.
Thank you, Izabela, for putting that up.
Gotta do the crab now, too.
Maybe. We can almost do M35. There it is, right there. Or is that it? Oh, there's two. I think this is it right here. Alright, I gotta move up to it now. There we go. This is a beautiful flaming star nebula. It's a nebula that encompasses a number of light years in every direction, and it's associated with this star. And the star is creating an emission nebula, and there's dust that is reflecting light and scattering the light to make that reflection nebula that we talk about so often. We're gonna just move the telescope a little bit to the east to center it up. Okay. And this is going to be a beautiful object, I can tell you that. It is going to be nice. Now, let's just get this straightened out. We're going to set this. We're going to do get our search here. Get our guide star here in a sec. Searching, the obligatory 13, 14 seconds or so. There we go. Start the calibration. Off we go. And now we're going to do another 40-second shot at 400 gain. So this is going to be a pretty high shot. Okay, so let's start this one in right now. We have a stable guide. I'm taking advantage of no wind out there, guys. Clear. All right.
Do you have your temperature compensation on now?
I do.
Okay.
It's 7.81 degrees Celsius now.
It's in the 40s.
Yep. It's 44.6 actually, so yeah. Alright. So we started with that. Doesn't look like much, but if you look at our black level here, it's totally to the right of the curve, meaning that all this data is missing from there. So if we have it move it over, now you see a tremendous extent of what's there. Okay. And we'll just get rid of this curve so you can actually see it. Alright, and now we're going to come in and do a color correction. And now we see the Flaming Star Nebula. Yes, there's more down south, of course. But the Flaming Star Nebula itself is here. And let's do this.
Oh, Alpha Centauri Virgo.
Yeah, I'm going to do something else. I'm going to come back here for a second. And I'm going to move us a little bit up in the field because I want to capture something else in addition. Hey there, Alpha Centauri. How you doing? We're going to go south here a little bit.
Dean, Marc talked about reflection nebulosity earlier tonight. It's blue due to what's called Rayleigh scattering.
Yeah.
Same reason Earth's atmosphere looks blue. As a general thing, yeah, all reflection nebula is blue in color. I guess that's a fair statement, isn't it?
Yeah, that's right. And if you think about it, think about volcanic eruptions that spew a lot of ash, dust into the air. Volcanic sunsets are a deep red color, and that's because they also are very effective at scattering blue light. Just like the reflection nebula we see, those are dust particles that are scattering the blue light. So the blue light is being scattered I might have said scattering red light. I think I meant scattering blue light. The volcanic particles will scatter the blue light from the sun, making them even redder, which is really impressive. But when you see a volcanic sunset, it means there's many, many particles up in the atmosphere now that you got to deal with when it comes time to take pictures and stuff like that, and that could just be awful.
Volcanic sunsets are often purple.
Well, they're actually volcanic sunsets tend to be very red when you're looking at the upper stratosphere particles. I mean, I haven't seen a purple volcanic sunset. Have you?
Yes.
I have not. But if you think about it, blue light and red light makes that magenta purple light. So I don't understand why a volcanic sunset would appear purple. But obviously, if it does, it does. But it is scattering a lot of... That's what I wanted to do. It's scattering a lot of light. A lot of blue light. Look at that nebula. Let's make sure focus is still intact. Oh, the focus looks great. This is good. So our temperature compensation is working. What eruption did you see that had a purple sunset?
Oh, I don't remember what it was. Some of it is just what I've read. I have seen Pinatubo was purple. I've read they say that volcanic sunsets are often purple.
Okay.
I remember Pinatubo in particular.
Okay. We'll have to look that up and figure out the physics of why that particular eruption was purple. Because volcanic sunsets do what reflection nebulae do, but on steroids over the atmospheric molecules. But maybe it has to do with the relative density of the air versus the particulates in the atmosphere. More or less can make it either red or possibly fewer particles in the air. If once they thin out, it might add a red component to the blue light and make it look kind of a purpley. But I've seen a volcanic sunset as well, and it was startlingly red. I mean, redder than my light. I mean, we're looking at very, very red. Okay, Izabela is talking about purple lava. That's actually something else. That's burning sulfur. I actually did a what show? Oh, I remember. It was The Proof Is Out There on A&E. When I was I do a lot of those shows, and in The Proof Is Out There, I talked about blue lava. And actually, I figured that one of the things captured as lights on a volcano that were blue was actually a burning sulfur particles coming down the side of the volcano that made blue lava. It's very rare. Indonesian volcanoes show it as well. Very interesting stuff.
I think you answered it yourself earlier. The purplish hue is produced when fine volcanic aerosols reach the stratosphere and scatter blue light, which when mixed with ordinary sunset red produces a violet tone.
Okay.
The purple is often preceded by a yellow arch hugging the horizon.
Okay. So it has to do with the diminishing density at altitude.
Whatever. There are plenty of pictures of it on Google.
Okay. So this is the Flaming Star Nebula. Obviously named so because it appears the star is flaming. In fact, it's an emission nebula, but if you notice, inside this area, there are a lot of really cool reflection nebula tendrils in here that dominate the area over the hydrogen emission for a period of time. This is interesting too. There's a very bright hydrogen emission location right here. Really pretty. And this nebula here, right, coming down, this will continue on down to more nebulae down below. But we're only doing this one tonight. We're not going to hit any of the others. Just try to give it a little more. Let's see what this will show us. How much more detail is here? Okay, so you got more there. This is really pretty, Daryl.
Mm-hmm.
Izabela's not a big fan of the flaming star. That's okay. I don't hate you for it. Yeah, this star is responsible in part for causing a lot of this emission nebula here. Sharp divisions too, at least they appear sharp only because we're so far away. We get closer and they'll be gradual and mixed in with more. Like clouds. Yeah, this is really pretty. And this will be our last object tonight.
You don't want to try 1097?
I do, but oh, you mean the galaxy? Remember I guess it's probably up now, and it's in the direction of parking, so I guess we could do it as a last thing.
Okay.
Yeah. Yeah. Thanks for reminding me. That's a good object to try, actually.
All right. Sky and Telescope magazine said volcanoes turn twilights purple. So there.
Okay. You want a cookie?
What?
You can have a cookie. I've actually, I've only looked at, I think again it has to do with the density, like we were talking about before, but I do
One
think,
article said it's due to sulfur.
okay, I have to look that up. I don't know. Cosmic Ray says, how about Magic Marc's adult astronomical coloring book? I'm not even sure I want to pursue that, Cosmic Ray. I mean, I think it'd be kind of boring for people to try and do color by number on something like this, huh?
Adult coloring books were huge a few years ago.
That's true. I actually sort of remember that. Interesting. Oh, James Dugan down in Australia. He's got the Magellanic Clouds, you know, and the southern Milky Way over his head, practically. So, I'm telling you, that's got to be something down there. I have a few people that I know that are in Australia, but I've never approached them and asked them about putting an STLS down there. I've actually thought about it. Have a Southern Hemisphere telescope. Then no one can ever say that, you know, there has to be a down day for streaming because while it's daytime here, it's nighttime there. We can stream Australia all day long, and stream Arizona all night long.
Never get any sleep.
Sleep is overrated. I mean, yes. What? That's true. You are right. Let's do this. Okay, let's bring this in full screen. Wow. Move this out of the way. Okay, that's a beautiful image right there. Izabela, I'll win you over with the nebula here. I know you're not a big fan. I'm not sure why. Yeah, I've heard of Dylan O'Donnell.
He strikes me as kind of a jerk.
Okay, let's not talk about other people on the stream.
Well, he does.
Well,
Thank you, Justin.
Justin T, man, hey, thank you. Thanks, brother. That's very kind of you.
Excuse me.
Okay, so Cosmic Ray and Izabela, you guys have to figure out why you can't see each other, because it's not up to me. I haven't done anything with this. Okay, we have 16 stacked here at 40 seconds apiece. We're getting some nice detail in here that we haven't seen before. Wow. James Dugan says, yeah, okay. I get you, basically. I think he's funny, but I'm kind of biased. I'm an Aussie. You're an Aussie. Yeah, Cosmic Ray says I've been trying everything here, and he's talking about trying to see Izabela's commentary. I don't know why you can't see her. You know what? Google is your friend. Why not look up in Google, how come I can't see someone in chat, and see if there's a way that'll bring you around into trying to figure that out. Uh-oh, Simon Thompson's registered an opinion. I think Simon's with you, Daryl.
Yeah, I guess I'm a troublemaker.
Nah. You have an opinion. Everyone's allowed an opinion. Let's see here. Okay. Well, as you can see, we started out with about, this much nebulous detail, but now there's nebula all throughout this entire image. You notice that? It's everywhere in here. It's everywhere. I can't stop it. It won't go away. Wow. Let's bring our telescope back here. I want to see that. Okay, telescope is doing fine there. That's about as far as we can go tonight with looking that direction. So, one more. We go to 20 and we'll stop. And we're almost there. We're in 3, 2, 1. And we will pause it at 20. There we go. And I will save it after I name it. So this is the flaming star. What? What?
He said, I'm not a bum, I'm a jerk. Steve Martin.
Yeah. He hates these cans. Remember that guy was trying to kill Navin Johnson?
There are snails on her plate.
Yes, sir. That's escargot.
Bring us some fresh wine.
This is old. All right. Oh yeah. He had no idea. Okay. Let me start Nebula. Now we can come in here and save it. And that's saved. And now we'll save it exactly as seen, so you can get the print of it, or there actually the this exactly as it is. Let's just zoom in one last time at the central region. Look at this. Look how beautiful that is. That's so delicate in there. You know, look at this right here. Notice that that's probably one of the most special locations in this entire region. You've got a dark globule in here that's surrounded by enough dust that it's actually still scattering the light from the star. But within it, there's a globule forming that is probably going to form another star someday, or possibly a star with some planets. That's pretty incredible. And any of this modeling you see, I can remove the noise. Very cool. All the details. Okay.
In this case, that bright star looks like it really is what's lighting up the inner part of it.
It does. And I think that is responsible for that. But, alright. Now let's go to Daryl's object. He asked for, I think, before he even started, he wanted to see it. Well, he knew we couldn't see it because it wasn't up yet.
Right.
But we wanted to.
It transits for you, I think, about 11:30.
Yeah, and it's almost that now. Out there.
Yeah.
All right.
Transit here about 11.
All right, so let's come out here. We're going to go into the constellation of the Furnace.
I can't guarantee anything with this one, folks. This was an excellent APOD yesterday, and then I looked it up elsewhere, and it's a beautiful barred spiral galaxy.
And we'll see what it looks like.
I remember correctly, it's gravitationally interacting.
All right, so now...
Should be due south.
Yeah. So Sculptor is already setting, and that means that Fornax is right here. And we go into Fornax, there's Eridanus, the river. There's lots of galaxies in here. So I guess I should just look it up to get the right one, huh? Otherwise I can just keep...
There's quite a group of them there.
Yeah. I don't know if we can see those. Let's see how the height is here. There's still only 15 degrees. A little bit to the southeast. I'm not sure. Oh, the colossal cosmic eye is what... One of these was called the colossal cosmic eye. That's weird. Okay.
Did you see 1097?
Yep. And you see 1097? Okay, so there it is. Well, let's go there and see if we can see it. In the past, the telescope would try to find a waypoint star, and if it couldn't, it would start hunting around, which could cause problems. But I removed that hunting because we don't need to use it. This doesn't appear to require it. It's literally looking like it's trying to park the telescope, but we're gonna be okay. We're still looking above that. Was that it right there? That might be it.
Looks like the scope stopped short.
No, it's waiting for Starlink.
Oh.
Okay, so there it is. We have delays with Starlink every now and then. Alright. And coming from all the way across the sky, that's not so bad. Alright. So we're here. But we want to be... Let's tie it to the scope. for a second. And so we're actually, I believe that's it. That sort of looks like what you were showing me for the picture, yes?
I'm not sure.
Okay. Well, we'll find out when we take a picture of it. The more north we can go, the better it works for us. Okay. All right, that looks good. All right, so we're gonna search for our guide stars, you'll see, and then away we go. All right. So this object now is called NGC 1097. It's a galaxy in the constellation of the Furnace, which is Fornax. You know, some of these constellations you just don't expect to ever find anything in, but they sometimes surprise you. All right, this one won't be more than what do you think, 25 seconds? It's small, so it's probably going to be fine. It's visible now, so 25 seconds is probably all we need for this. Let's pop out of this, go into our stack, and see what happens in 20 seconds.
Oh, it's interesting in the APOD image.
Thanks, DK. Yeah.
I doubt your scope will show it, but
Look at that.
wow. The APOD showed, it said 4, I only saw 3, kind of like rays coming out of it that may have been like star streams.
Yeah. This is a barred spiral, guys, so you see this long extended nucleus in here, and it's off of that bar that the spiral arms come. And now with this second stacked image, a lot of the noise goes away, and you can start to see that really pretty. Let me do a color correction so the blue haze goes away. Here we go. That's what it's supposed to be. Wow. I don't think I ever saw this one, Daryl. I think this is the first time we saw this.
I think so.
Okay. Well, we're gonna have to be looking at it.
And there's actually a small companion galaxy at about 1:30 or 2 o'clock.
That's this guy right here, it looks like.
Looks like it's inside the arms of the main galaxy. Yes. We're barely seeing it.
I think, isn't that it right there?
I think so, yes.
And this is interesting. This is a blue dot right here. Is this galaxy currently having undergoing a supernova by any chance? This looks like it could be a supernova in the galaxy. Just because of the blue color. I mean, this is slightly blue. It could be a color correction thing. Let me color correct again.
Interesting. I see that in the APOD image.
Okay. So it belongs here.
It's not that bright.
Okay. Very nice. This might be a blue star at some distance to us. So, it might belong there. That knows what you're saying.
And it's a safer galaxy.
Hmm.
Nucleus also harbors a supermassive black hole.
I wonder if most galaxies actually are harboring supermassive black holes, which is why they're galaxies at all, maybe.
Oh, yeah.
That's a thought of mine. I brought that up with a lot of astronomers in the past, about black holes. And, in the past, there wasn't a whole lot of knowledge about black holes and so forth. So it was basically, they were like, well, anything could happen, or maybe, because what are they going to say? They don't know they can't say no. And I was just postulating a possibility. I wasn't saying that's what was there. But, we suspected as a group that there was probably something to that anyway. So it wasn't like it was a revelation on my part. A lot of people were saying it. This is coming in better.
It is.
As the time is going on, you can see some details in here.
Yeah, right where that blue star is at 2 o'clock, you mentioned, you see a dark lane.
Right here.
Yeah.
Yeah. There's another one there. This actually is sort of what they say our galaxy is. They say our galaxy is one of these hybrid galaxies. It actually is a spiral, but a barred spiral as well. So we have multiple spiral arms, just like this one, but many of the barred spirals will tend to have one major spiral arm coming off one side and one major spiral arm coming off the other. This one, on the other hand, has another spiral arm here, or this could be a continuation of this spiral arm. I'm not sure. And then this one probably comes down here.
Yeah, if that galaxy up at about 1:30 is interacting, I mean, it looks like that's what's distorted that right-hand spiral arm.
Let's see what else is there.
It's all spread out so much.
We're going to see what else is here now. Okay.
Well, that is. See all that fuzz pulled out on that right-hand spiral arm?
Yeah, right here.
Oh. Yeah,
yep.
Toward the inside of it.
Yeah. So maybe we're actually looking at a spiral arm that is being roughhoused by this additional galaxy here.
Yeah, sort of like the whirlpool.
Yeah. Very cool. All right, let's keep going here. We've got 13 stacked. Very interesting. I'm going to zoom in a little more because I want to look at something right here. I guess that could be a star in there, not a nebula. Is too faint to tell.
There is an H2 region there.
Oh, then we're seeing it then.
Yeah.
Yeah, I've never watched it. I never looked at this, so I don't know. That's cool.
Now, there's a number of H2 regions.
You see one right there too then. Is there one there? This
looks like it.
Is this a star, or is this just a very bright H2 region? It looks like a star. I see a bunch of H2 regions right here.
That one, I think, at about 10:30 o'clock in the spiral arm, that appears to be a star.
This one here.
Yes.
Okay, so then there's a reddish haze in here. It looks like spiral arm. H2 regions. I see some in here. There's one right here, it looks like. I think there's a lot right in here I can't really quite see yet.
Yeah. If you get a chance, take a look at that A-pod I sent you.
Okay.
There's actually quite a few H2 regions.
I believe it. I believe it. Okay. So now when you do this, now you can see that this spiral arm is actually, it's spread here, and it's got a, it's like it's wafting this way as it curves around. This one curves around, and it looks like a large amount of mass is being affected by this satellite galaxy, perhaps.
Yeah.
Wow.
Would longer exposures benefit?
Maybe we would see what we just saw. You know, we would see this, but without as much noise. So yeah, I think what would benefit the most, though, is if we had a camera with smaller pixels to do that. So
this is probably another one benefit from more focal length.
yeah, without a doubt, I think you're right.
Well, thank you for indulging me.
Yeah, no, it's beautiful. You can see some blue star clouds here.
Yeah.
So, and there's definitely a knot of them up here with some H2 region.
Yeah. That blue star cloud you mentioned is very prominent in the APOD image.
Okay, this one you're talking about.
Yes.
Yeah. Well, we've only got, we've stacked 22. And so that's pretty cool. This is nice. So we're going to, I'm going to save it now anyway. And let it keep stacking. All right.
Yeah, if you look at the APOD, there are several straight lines of stars running out from it.
Okay.
Like rays or something. The caption says 4. I only see 3. Izabela noted that one of them up to the upper left appears to have a crook or a break in it. It sort of comes out straight, then it turns 90 degrees.
Did you put the link in the Skype chat? Because I don't see it.
I did.
Did you put it under the other conversation with Izabela?
It's in the Skype chat? Yes, it's in the Skype chat. Give me just a second and I'll drop it into your chat here.
Okay. That's the one I was talking about, the one that was just you and me. All right, you're putting something in now, okay. This is getting clearer and better, look at that.
Oh, that's YouTube, that's not right.
This is getting good, so this is going to refine even more. Not bad, I'm telling you. This down a little bit. I can see a dark lane in here.
Okay, there it is. It's in your chat.
Okay, thanks. I see a dark lane in here. That's cool. Wow. So it has these mysterious jets. Let's see if we can identify these. Can't really see them. Boy, this is a crazy galaxy. Oh, I see a stream right here. There's a stream coming up right here. You see it? Very faint, but it's there. So there's a stream of stars that looks like it's coming up here, and there's a stream here that I can't really see on my exposure here. And there's another one coming out the bottom. Wow. I'm reading something here. 1 second, guys. Okay. Yeah, galaxies that have active nuclei, like this one, will do crazy things, like have jets sticking out of them, and jets of high energy material moving out at a good fraction of the speed of light. Or they may actually have radio jets and radio frequencies. You'd see these jets of radio energy coming out. Radio is electromagnetic energy, right? Which is light. This is pretty. Okay, this is where we stop. This is 32. So I'll pause it. I've got NGC 1097. I'll say save. And then I'll say save exactly as seen. And I have to say, the guiding tonight was perfect. Didn't have any problems with it. As I said before, we do more and more. That it gets so well refined. It gets to be a well-oiled machine. So that is cool. All right, so.
Well, thank you for indulging me.
Yeah, there's no problem.
That's cool galaxy.
Yeah. Wow. Okay. All right, guys. Well, this is looking good. I will say this. I want to thank you for coming. You can start to hear that music. That music means we've come to the end of another. We heard it at the beginning and we heard it at the end. Wonderful SkyTour live stream with our co-host Daryl Mason. Daryl, thank you so much for coming out and enjoying the night here with us.
Sure.
And all of you, thank you for being here. And just keep in mind that when you look at a galaxy image like this, you have to say to yourself, I wonder how many of them in that galaxy are looking back at us and asking the same questions. What else is out there? Would that be cool if we could figure that out with SkyTour Livestream and all of you? Well, anyway, guys, you have a good night, and we will talk to you soon. Good night, everybody.
Good night, all.